JUnit Architecture. Here you can see the detailed picture of the JUnit architecture. JUnit is a unit testing framework for the Java programming language. JUnit has been important in the development of test-driven development and is one of a family of unit testing frameworks which is collectively known as XUnit that originated with SUnit. Here you can see the detailed picture of the JUnit architecture. Detailing at the level of jar files, here the test API provides the facilities for different test engines. JUnit Jupyter API for JUnit 5 tests, JUnit 4.12 for legacy test here, and custom engine for third-party tests. Test engines mentioned earlier are created by extending the JUnit platform engine public API, which is part of the JUnit 5 platform. junit-platform-launcher public API provides the facilities to discover tests inside JUnit 5 platform for build tools such as Maven or Gradle or for IDEs. Besides modular architecture, JUnit 5 provides the extension mechanism which is extension mechanism. The architecture of a system strongly determines the capabilities and its behavior. Consider the runners and rules analyzed. The way of working is generated by JUnit 4 architecture that represent their foundation. Understanding the architecture of both JUnit 4 and JUnit 5 help us apply their capabilities in practice, write efficient tests, and analyze the alternative implementations, thereby quickening the phase at which we master unit testing. Here you can see old test JUnit is connected to Vintage. Inside Vintage, here you can see JUnit 4.12 and junit-vintage-engine. Here the old test JUnit is connected to here JUnit 4.12 here in this diagram, and here the vintage engine is connected to JUnit 4.12 here. Here the old test JUnit 5 is connected to Jupyter, and here the is also connected to JUnit-jupiter-api. junit-jupiter-engine is connected to JUnit-jupiter-api here. JUnit-jupiter-api and JUnit-jupiter-engine are inside Jupyter. Here other tests are connected to third party. Here other tests are connected to custom API, and custom engine is connected to custom API and custom engine are inside third party. Here the JUnit vintage engine, JUnit Jupyter engine and custom engine are connected to platform here and interacts with the JUnit platform engine. junit-platform-engine, junit-platform-launcher, junit-platform-runner, junit-platform-surefire-provider, junit-platform-gradle-plugin, junit-platform-console, and junit-platform-console are inside platform. Here junit-platform-runner and junit-platform-surefire-provider and junit-platform-gradle-plugin and junit-platform-console are connected to junit-platform-launcher. Junit-platform-launcher is connected to junit-platform-engine. And here junit-platform-runner is connected to vintage here. And here the IDE or build tools are connected to platform here, and then platform junit-platform-launcher. Here the junit 4.12 and junit-jupiter-api and custom API are test APIs. Here the junit-vintage-engine, junit-jupiter-engine, custom engine, and junit-platform-engine are test engines. And here the junit-platform-launcher, junit-platform-runner, junit-platform-surefire-provider, junit-platform-gradle-plugin, and junit-platform-console are test launchers. Here you can see the interfaces, and these arrows are implying usages. And here you can see the extensions with these arrows, extensions with JUnit platform engine here. Here you can see the monolithic architecture of JUnit 4, a single jar file. JUnit 4, released in 2006, has a simple monolithic architecture. All its functionality is concentrated inside the single jar file. If a programmer wants to use JUnit 4 in a project, all they need to do is add that jar file on the class path. Here you can see junit.jar file. Here you can see the modular architecture of JUnit 5. A new modular approach was needed to allow the evolution of JUnit framework. The architecture had to allow JUnit to interact with different programmatic clients that use different tools and IDEs. The logical separation of concerns required an API to write tests dedicated mainly to developers, a mechanism for discovering and running the tests, an API to allow easy interaction with IDEs and tools and to run the test from them. As a consequence, the JUnit 5 architecture contains 3 modules: JUnit platform, which serves as a foundation for launching testing frameworks on the Java Virtual Machine JVM. It also provides an API to launch tests from the console, IDEs, or build tools. JUnit-Jupiter, the combination of the new programming and extension model for writing tests and extensions in JUnit 5. The name comes from the 5th planet of our solar system, which is also the largest. JUnit Vintage, a test engine for running JUnit 3 and JUnit 4 based tests on the platform, ensuring backward compatibility. Here you can see JUnit platform, JUnit Jupyter, and JUnit Vintage. Here you can see the big picture of the JUnit architecture. Here all test is connected to Vintage, new test is connected to Jupyter, another test is connected to third party, and third party is connected to platform. In JUnit, here in JUnit 5, Vintage, Jupyter, and platform is there. Vintage is connected to platform, Jupyter is connected to platform. IDEs and build tools are connected to platform. Here you can see the JUnit 5 technology application architecture. JUnit 5 is a rewrite of JUnit. The following three key building blocks of JUnit 5, along with support for the custom testing framework, which along with their components are represented in this diagram. JUnit platform, JUnit Jupyter, and JUnit Vintage. Unlike earlier versions of JUnit, JUnit 5 has been split into following three sub-projects in addition to the great flexibility of plugging in one's own custom framework, custom testing engine framework. JUnit platform. JUnit platform is the foundation building blocks of JUnit 5. The most important feature of JUnit platform, which make stand out, is the ability to allow the custom testing framework engine to be plugged in through the testing API. This very capability, the testing API of the platform, allows support for running JUnit test using JUnit 5 testing engine, Jupyter, or any other custom test engine. The following are some of key platform components: testing API for plugging in the custom developed test engine, console launcher for discovering and executing tests from the console, Gradle and Maven plugin support for discovering and executing test, runner to allow execution of JUnit test in the JUnit 4 environment, JUnit Jupyter. This provides a test engine for running unit test written with JUnit 5. The following are some of the key aspects of JUnit Jupyter: programming and extension model for writing unit test and extensions, support for migrating unit test written with Java 4 to Java 4 to Jupyter. JUnit Jupyter. New assertion methods which work with Java 8 lambdas. Support for annotations such as ampersand display name, which allow custom display names consisting of spaces, emojis, special character, and so on. JUnit Vintage provides a test engine for running unit tests written with earlier JUnit versions such as JUnit 3 and JUnit 4. Here you can see a JUnit test connected to junit-jupiter and JUnit vintage and JUnit and custom testing framework. In JUnit programming model, extension model, migration support and new assertions annotation are in JUnit Jupiter. JUnit 3 support, JUnit 4 support and JUnit 4 support are in JUnit vintage. Here custom testing framework. Testing API, junit-platform-runner, platform-launcher, Maven, Gradle-plugin supports are in JUnit platform. Eclipse IDE, Jenkins, Maven, Gradle and IntelliJ are connected to JUnit platform here. Here you can see the JUnit 5 architecture in a different view. JUnit 5 comprises several building blocks. The architecture of JUnit 5 is illustrated here. Let's discover some core elements of this architecture. JUnit platform, its main responsibility is to launch testing frameworks on the JVM. As you see in the architecture diagram, it is an interface between build tools, tests, IDE and JUnit. It also defines test engine API to create a testing framework which operates on JUnit platform. And in this way, we can use external libraries in JUnit ecosystem by implementing custom engines. junit-jupiter. This is the new extension and building block of JUnit. It comprises new extensions and libraries for JUnit 5. The new annotations of the JUnit 5 are summarized as follows. At before all, annotated method runs before all test methods in the current class. At after all, annotated method runs after all the test methods in the current class. At before each, annotated method runs before each test method. At after each, annotated method runs after each test method. At disable a test class or a method. At tag, we can tag the test methods such as smoke, regression, critical, etc. At nested, annotated class is a nested non-static test class. At display name, we can declare a custom display name for a test class or a test method. At extended with, it is used to register custom extensions. At test factory, declare a method that is a test factory method for dynamic testing. JUnit vintage, it is supporting library for JUnit 5. By using JUnit vintage, we can also run JUnit 3 and JUnit 4 based test on JUnit 5 platform. JUnit 5, yeah. Here you can see junit-jupiter and JUnit vintage and JUnit and custom engine are connected to JUnit test engine interface here. JUnit vintage is connected to JUnit 4 and the custom engine is connected to another framework here. Here JUnit 4 is and another frameworks are and JUnit-jupiter, JUnit vintage, custom engine and test engine interface are here in the engines. Here the JUnit platform is in platform. Test engine interface is connected to JUnit platform. Here the IDE and build tools are connected to JUnit platform. IDEs connected to your tests, and build tools are connected to your test here. Here you can see JUnit for in modularity. First of all, JUnit 4 is not modular as depicted in this picture. The architecture of JUnit 4 is completely monolithic. All capabilities of JUnit 4 are provided by the junit.jar dependency. As a result, different test mechanisms such as test discovery and execution are tightly coupled in JUnit 4. Johan's link, one of the JUnit 5 core team members, summarizes this problem in an interview with JAX magazine on August 13, 2015 during the inception of JUnit 5. The success of JUnit as a platform prevents the development of JUnit as a test tool. The basic problem we want to solve is executing test classes by separating a sufficiently powerful and stable API. Here tests are connected to junit.jar, and here tests are connected to extensions. Extensions are connected to junit.jar, and third-party frameworks are connected to junit.jar. IDEs and build tools are also connected to junit.jar. Here you can see the structure of JUnit version 3.7. This figure shows version 3.7, and perhaps one aspect seems most striking. The diagram is lovely. We can see at a glance, for example, AWT UI depends only on runner and framework. A consumable lot programmers value such clarity, drawing from it a warm sense of no overtimeness. We should not, of course, read too much into package diagram. We do not know, for example, whether runner package hold 500 or 5 million lines of code. Deeper investigation will show that no monsters lie hidden under beds here, but we shall confine ourselves mostly to structure for the moment. Structure being a set of elements and their dependencies, most would conclude that JUnit version 3.7 is well structured work. Here the UI is connected to AWT UI and runner, and AWT UI is connected to runner and framework and UI. Here the runner is connected to UI, AWT, framework, text UI, swing UI, and here swing UI interacts with runner, framework, and extensions. Here the text UI is interacts with runner and framework. Here extensions are interacting with swing UI and framework, and here framework interacts with AWT UI, runner, swing UI, text UI, and extensions. Now we are considering the structure of JUnit version 3.8. Let us move on to version 3.8. The version 3.8, the UI package has packed its bugs, but otherwise the structure is unchanged. If anything, it appears even more aesthetically pleasing than before. Some might consider this figure a thing of beauty. Uglier constructions certainly besmirch half the t-shirts that amble by you daily. So far so good. Here the text UI interacts with the framework and runner, and Swing UI interacts with extension, framework and runner, and AW2 UI interacts with framework and runner. Here the extensions interacts with Swing UI and framework, and runner interacts with AW2 UI, Swing UI, text UI and framework interacts with extensions, text UI, Swing UI, AW2 UI and runner. Now we are considering with the structure of JUnit version 4.0. The version 3.9 was not in the repository. Something has happened in version 4.0. The diagram is still relatively clean looking despite the number of packages having almost doubled from 6 to 11. A nagging doubt was surfaced, however, in some qualitative way, the elegance of version 3.8 has, if not been lost, at least suffering from some tarnishing. Curved lines have appeared indicating our first dependency is going up. The package in itself, this is insignificant. Spoikling's algorithm produces such curves as artifacts rather than damning moral judgments. A curve line only raises concern where it forms the infamous bow pattern of mutually dependent elements, and such, alas, is the case here. Mutually dependent packages invite suspicion. Mutually dependent packages suggest exposure to one another's ripple effect changes, and this doubles programmers. This figure reveals such bows, runners, framework, runners, framework notifications, still package structure look manageable, and concerns are allied with release 4.1, whose structure is identical with that of version 4.0. Here the runners are connected to runners and runner and JUnit, and here text UI is connected to runner and framework. Here runners are connected to runners, JUnit, requests, notification, framework, runner and extensions. The JUnit is here connected to interact with the runners and runners here. Here the runner interacts with the runners are here, and request and runner and framework. Here the runner interacts with the text UI, framework and runner. Here the framework interacts with the runner, runners here, and text UI and runner here, and extensions and manipulation and notification, and the runner here. Here the request interacts with runners, runner here, and manipulation. Here the notification interacts with runners and runner here and framework here. Here the extension interacts with framework and runners here, and manipulation interacts with requests, runner and framework. Here you can see the structure of JUnit version 4.2. Let us move on to 4.2 now. The version 4.2 is almost similar to 4.0. A single new package is added, internal. The bows that arrived with version 4.0 have failed to metastaticize. Structural degradation appears arrested. Version 4.3 however is growling around the corner. Here the runners interacts with JUnit runner and runners here, and text UI interacts with the runner and framework. Here the runners interacts with runners here and JUnit and request and manipulation and framework and notification and extensions. Here the JUnit interacts with runners and runners here and internal. Here the runner interacts with the runners here and request and runner and framework and notification. Here the runner interacts with the text UI and runner here and framework here and requests. Here the framework interacts with the text UI and runner and runners here and manipulation and notification and extensions. Here the request interacts with runners, runner here and manipulation, and internal interacts with JUnit. Notification interacts with runner and runners here and framework, and extension interacts with runners here and framework. Here you can see the structure of JUnit version 4.3. The 4.3 represents by far the largest structural change in the history studied here. Beneath the surface, the number of functions leaps from 564 in version 4.2 to 1309 in version 4.3. It will fall almost as dramatically the next release. Though the number of packages arises from even just 16, this is non-commensurate rise in the number of packages may help explain the fall in configuration efficiently from 31% to just 18%. The introduction of tests package seems the most significant change, yet the authors have performed this introduction quite successfully. A good test of a structure is easy, with which one can point to any element and identify other elements it depends on directly and transitively. Though there are many test dependencies are readily traceable. Also, we note the number of bows remain unchanged. The surge of functions has not triggered an increase in mutually dependent packages. Here the money interacts with JUnit and framework. Here test interacts with text UI, extensions, manipulation, requests, framework, runner, notification, runners here, and JUnit and runners here. Here samples interacts with text UI, framework, and JUnit. Here you can see another package. Text UI interacts with tests here, and runner and framework. Here runners interacts with runners here, and test here, and extensions here, and manipulation and framework, and runner here, and notification here, and JUnit here. Here extension interacts with the runners here, and test UI, and test here, and framework. Here the JUnit interacts with runners, samples, tests, runners, and money here. And here framework interacts with samples, runners, tests, money, extensions, requests, runner here, and notification here. Here runner interacts with runners here, and tests, and framework, and request, and manipulation, and runner, and notification. Here the request interacts with runner, and framework, and tests, and manipulation, and runner, and notification. Here manipulation interacts with runners, and test. Here the notification interacts with runner, and runners, and tests, and runner, and requests. Here runner interacts with runner, requests, and tests. Here internal interacts with JUnit. Here you can see the structure of JUnit version 4.4. This figure shows the version 4.4, and tests leaves as before. Before we really got to know it. The number of functions fall from 1309 to 853. The number of packages rises to 19. Among the new packages to make their entrance are the Hemcrust cluster, which also unfortunately brings 3 more mutually dependent packages to the party. Still, this cluster sheets from main group. We may have some difficulty counting the number of bows in the main group. But the diligent programmer could still hope to identify all transitive dependencies from a randomly chosen target. This is perhaps the last time that such is the case. Here the runners are connected to runners interacts with runners here, and runner here, and JUnit here. The results interacts with internal, and runner, and notification, and Hemcrest. Here text UI interacts with theories, and runner, and here supplies interacts with theories. Here theories interacts with text UI, runner, framework, internal, and runner interacts with theories, results, runners here, and framework, and internal, and manipulation, and notification, and runner. Here runners interacts with runner, and runner. Here runner interacts with text UI, runner, and framework. Here framework interacts with runner, runners, and here JUnit interacts with runners, internal and internal. Here the internal interacts with JUnit runner, and here Hamcrest interacts with JUnit results, matches, core and internal. Here notification interacts with runner, results, runner, framework, internal, requests. Here request interacts with notification, runner, runners and manipulation. Here the internal interacts with the JUnit, theories and framework. Here extension interacts with framework and runners. Here matches interacts with Hamcrest, JUnit. Here internal interacts with Hamcrest. Here the manipulation interacts with runner, runners, framework and request. Here core interacts with Hamcrest and matches. Here you can see the structure of JUnit version 4.5. A difficulty of tracing transitive dependencies characterizes the last paste of JUnit package structure. This figure shows the version 4.5. 150 functions more than version 4.4. The system boasts a configuration efficiency risen from 29% to 34%. Its 26 packages, however, have become embroiled. For the first time, the programmer introduced to this system might pause before accepting the assignment. Note that the drawing algorithm generating the diagram must take some blame. A better algorithm might do a better job. No algorithm, however, can veil the brass rise in interconnectedness on display. Hamcrest previously to one side has gravitated towards the big players, tugged by new dependencies from both runner and internal. It will remain a center stage until its sudden elimination in version 4.11. How many mutually dependent packages do we have, and who can say if we change the package? Can we easily predict which client will be affected? Can say with any certainty which client will not be affected? Such questions dog all later revisions, so let us skip towards let us solve the intermediates are visible in animated graph. You can see the packages here. The matches interacts with matches here, and supplies interacts with here theories. Results interacts with internal, Hamcrest, runner and matches. Here text UI interacts with framework and runner. Here runners interacts with matches. Here theories interacts with suppliers, internal, JUnit, core and runner here. Here the matches interacts with runners, results and matches here, and Hamcrest here and runner here and core here and runner here. Runner interacts with results here and internal here and Hamcrest here and manipulation here and runner here and notification here, runners here and runner here. Internal here interacts with runner, results and Hamcrest and core. Runner here interacts with the matches, runner here and theories and manipulation and core and JUnit and model and statement. Here Hamcrest interacts with the matches, runner, results, internal requests, core, here the framework interacts with runner, text UI and runner here, and notification and manipulation and builders and extensions. Here the notification interacts with framework, runner here, and results and runner here, and internal and model and builders and model here. Here the request interacts with runner here and hamcrest here, manipulation and runner here, and model here and builders here. Here internal interacts with theories and model here. Here core interacts with matches and theories and hamcrest. Here internal interacts with hamcrest. Here statement interacts with runners here and model here. Here the runners interacts with builders here and runners here and core here, and request here and model here. Manipulation interacts with runners here and runner here and request. Model interacts with statement here, runner here, notification here and builders here, and internal here and runner here and model here and JUnit here. Model interacts with model here, statement here and notification here and runner here and runners here. Extension interacts with framework here and runner. Here JUnit interacts with statement, model, and here notification and hamcrest, runners here and theories here and runners here. Here you can see the structure of JUnit version 4.11. By version 4.11, the transitive dependencies have proliferated seemingly unchecked. We are far from the short dependency chains and few cyclic dependencies of good structure. And this ultimately is the point. A software user experience realization is just another term for what software does. This user experience realization and its structure are, however, practically orthogonal. Perhaps hundreds of thousands of programmers use JUnit daily. It is a phenomenally well-tested piece of software and it works beautifully. Yet this tells us nothing about its structure. Structure is not about execution, it's about development cost. The greater the interconnectedness of a structure and more ripple effects can occur during updates and more costly those updates can grow. You cannot test good structure into a design. JUnit exemplified this. It was written test first, but its structure has nevertheless degraded significantly with time. Testing, at least unit and acceptance testing as we generally know them, is about user experience realization. We write unit tests such as verify what bank account balance does not fall below 0. We do not write unit tests such as verify that package A has no dependencies on package B, C, D, or Z, yet later is precisely the type of consideration we must take when we create a structure. Here you can see runners interacts with runners here, and here experimental interacts with model, runners and runner. Here categories interacts with model, runners, framework and runner. Here max interacts with runner, notification, runners here, and runner here. Results interacts with internal, model, and runner. Here text UI interacts with runner, framework. Here supply interacts with theories. Here theories interacts with supplier, max, runners, model, internal, and JUnit. Here runners interacts with theories, max, categories, experimental, runner here, and model, and statements here, and internal, and model, and notification here, and rules, JUnit rules, runners, and runner. Here runner interacts with results, max, categories, experimental, runner, model, internal, runners, a framework. Here runner interacts with runner, text UI, and here runners interacts with runner, runner. Here model interacts with runners, runners, theories, categories, experimental, and requests, statements, internal, model, and rules, and rules here. Here framework interacts with text UI, runner here, and runners here, and internal, and notification, and manipulation. Here internal interacts with runners here, and runner here, results, model, and requests, matches, model, and notification, and JUnit. Here manipulation interacts with runner, framework, categories, and runners here, and requests. Here the notification interacts with framework, runner, and results, max, runners, model, internal, model, and builders. Here request interacts with manipulation, internal, runner, and model. Here internal interacts with theories, model, and here model interacts with notification, model, and here rules interacts with model, and runners, and here rules interacts with runner, runners, and statements, JUnit, and here external extension interacts with framework, runners, and here statement interacts with rules, model, and runners. Here builders interacts with runner, runners, model, runners, and requests. Here JUnit interacts with internal, rules, theories, runners here, and model, and internal. Here matches interacts with the rules, and matches. Here matches interacts with rules, and matches, and internal. Here you can see test lifecycle phases. Normally the test class contains multiple test methods. JUnit manages the execution of each test method in a form of a lifecycle. The complete lifecycle of a test can be seen in 3 phases with the help of annotations. Setup. Setup. This phase puts the test infrastructure in place. JUnit provides class level setup before all, and method level setup at before each. Generally, heavy objects like database connections are created in class level setup, while lightweight objects like test objects are reset in the method level setup. 2. Test execution. In this phase, the test execution and assertion happen. The execution result will signify a success or failure. Cleanup. This phase is used to clean up a test infrastructure setup in the first phase. Just like setup, tear down also happen at class level after all and method level after each. Here the annotation interface before all in package org.junit-jupiter.api in module org.junit-jupiter.api. At before all is used to signal that the annotated method should be executed before all tests in the current test class. Annotation interface before each. At before each is used to signal that the annotated method should be executed before each at test, at repeated test, at parameterized test, repeated test, and at parameterized test, at test factory, and at test template method in the current test class. The annotation interface test. At test is used to signal that the annotated method is a test method. Annotation interface after each. After each is used to signal that the annotated method should be executed after each at test, at repeated test, at parameterized test, at text factory, and at test template method in the current test class. Annotation interface after all. At after all is used to signal that the annotated method should be executed after all tests in the current test class. Here you can see class level setup is connected to setup is connected to test execution is connected to cleanup is connected to class level cleanup, and cleanup is connected to setup again via repeat. And here the setup is connected to text execution is connected to cleanup again, and then cleanup is connected to setup via repeat, and cleanup is connected to class level cleanup in the end. Here you can see a sample project structure in JUnit testing for MySQL project in Java. Here you can as this is a Maven driven project. Here you can see pom.xml. Here the geeks for geeks.jdbc.com you can see, and it's under that source main Java and source main toast test Java and JR system library Maven dependency source and src target and pom.xml, and here source main under source name Java geek for geeks.jdbc.com and resources, and here geek.geekjdbc.com and there are connection.class.java, freelancer.java, and freelancer-queries.java. Here source test Java is there, and under that geek for geeks.jdbc jdbs.com, and under that apptest.java. Now we are focusing on all test JUnit. Here you can see the main differences between JUnit 3 and JUnit 4. In JUnit 4, the attest annotation contained in the package org.junit represent a test. Any public method can be annotated with attest to make it a test method. In order to set up the test fixture, JUnit 4 provides the before annotation. This annotation can be used in any public method. Similarly, any public method annotated with at after get executed after each test method execution. JUnit 4 provides two more annotations to enhance the test lifecycle: at before class and at after class. They are executed only once per test class before and after all tests respectively. This table summarizes the main differences between JUnit 3 and JUnit 4. Here the features, and here JUnit 3 and here JUnit 4. A test destination, here test XXX pattern, here at test annotation, here run before the first test, in JUnit not supported, here at before class annotation, here run after all tests, JUnit 3 not supported, in JUnit 4 at after class annotation, run before each test, in JUnit 3 override setup method, here JUnit 4 at before annotation, run after each test, in JUnit 3 override tear down method, in JUnit 4 at after annotation, ignore test, here JUnit 3 not supported, in JUnit 4 at ignore annotation. As an example, we can consider this code segment. Here the annotation type ignore. Sometimes you want to temporarily disable a test or a group of tests. Methods annotated with test that are also annotated with ignore at ignore will not be executed as tests. Also, you can annotate class containing test methods with at ampersand ignore, and none of the containing test will be executed. Native JUnit 4 test runners should report the number of ignored tests along with the number of tests that ran and the number of tests that failed. This annotation is available since version 4.0. In JUnit 5 we use annotation disabled, and annotation type ignore is in packaged org.junit. Here on the execution of the class file, the test JUnit _JUnit 1 is skipped during the execution. Besides, the method annotation annotated with ignore and all other test methods run as expected. Here you can see a screenshot of the console window proves the same. Here you can see the resultant run count shows 3 to 3 test cases, and one test case shows skipped. The run count shows 3 to 3 because even the skipped test case attempted to execute. Here annotation type test. The test annotation tells JUnit that the public void method to which it is attached can be run as a test case. To run the method, JUnit first constructs a fresh instance of the class, then invokes the annotated method. Any exceptions thrown by the test will be reported by JUnit as a failure. If no exceptions are thrown, the test is assumed to have succeeded. This is in JUnit 4. As an example 2, we can consider this junit-vintage-engine. Running JUnit 4 test on the JUnit platform here. Just make sure that the JUnit vintage engine here artifact is in your test runtime path. In that case, JUnit 3 and JUnit 4 test will automatically be picked up by the JUnit platform launcher. As an example 3, we can consider class is potential JUnit 4 test class in package org.junit.vintage.engine.discovery in module org.junit.vintage.engine. As an example, we can consider as an exception example, we can consider this code segment here. You can see the optional element expected. Optionally specify expected a throwable to cause a test method to succeed if and only if an exception of the specified class is thrown by the method. If a throwable message or one of its properties should be verified, the expected exception rule can be used instead. This is default to org.junit.test.none.class. The parameter expected declares that the test method should throw an exception. If it doesn't throw an exception, or if it throws a different exception than the one declared, the test fails. For example, here the following test succeeds. Using the parameter expected for exception testings comes with some limitations. Only the exceptions type can be checked, and it is not possible to precisely specify the code that throws the exception. Therefore, JUnit 4 has improved its support for exception testing with assert.assert_throws class throwing runnable and expected exception rule. With assert throws, the code that throws the exception can be precisely specified. If the exception's message or one of its properties should be verified, the expected exception rules can be used. As an error example, we can consider this in JUnit 4, tests pass, 2 tests fail, 2 tests cause an error in error and 8.4s com.mystuff.all test failed, unknown passed, etc., and unknown failed, unknown caused an error, etc. Now we are focusing on Vintage. JUnit Vintage provides a test engine for running JUnit 3 and JUnit 4 based tests on the platform. It requires JUnit 4.12 or later to be present on the class path or module path. Here you can see the monolithic architecture of JUnit 4, a single jar file, junit.jar. JUnit 4, released in 2006, has a simple monolithic architecture. All its functionality is concentrated inside a single jar file. A programmer wants to use JUnit 4 in a project. If a programmer wants to use JUnit 4 in a project, all they need to do is add that jar file on the class path. Here you can see junit.jar. Here you can see JUnit 3.8.x patterns summary. The goals of JUnit. What are the goals of JUnit? First, we have to get back to assumptions of development. If a program feature lacks of automated test, we assume it doesn't work. This seems much safer than prevailing assumption that if a developer assures us a program feature works, then it works now and forever. From this perspective, developers aren't done when they write and debug code. They must also write tests that demonstrate that the program works. However, everybody is too busy. They have too much to do. They don't have enough time to screw around with testing. So the number one goal is to write a framework within which we have some glimmer of hope that developers will actually write tests. The framework has to use familiar tools, so there is little new to learn. It has to require no more work than absolutely necessary to write a new test. It has to eliminate duplicated effort. If this was all test had to do, you would be done just by writing expressions in a debugger. However, this isn't sufficient for testing. Telling me that your program works now doesn't help me, because it doesn't assume me that your program will work 1 minute from now after I integrate, and it doesn't assure me that your program will still work in 5 years when you are long gone. So the second goal of testing is creating tests that retain their value over time. Someone other than the original author has to be able to execute the test and interpret the result. It should be possible to combine tests from various authors and run them together without fear of interference. Finally, it has to be possible to leverage existing tests to create new ones. Creating a setup or fixture is expensive, and a framework has to enable reusing features to run different tests. The The design of JUnit will be presented in a style first used in the idea to explain the design of a system by starting with nothing and applying patterns one after another until you have the architecture of the system. We will present the architectural problem to be solved, summarize the pattern that solved it, and then show how the patterns was applied to JUnit. Test case. First, we have to make an object to represent our basic concept, the test case. Developers often have test cases in mind, but they realize them in many different ways. Print statements, debugger expressions, test scripts. If we want to make manipulating test easy, we have to make them objects. This takes a test that was only implicit in the developer's mind and make it concrete, supporting our goals of creating tests that retain their value over time. At the same time, the object developers are used to well developing with objects, so the decision to make test into object supports our goal of making test writing more inviting, or at least less imposing. The command pattern fits our needs more nicely. Quoting from the intent, encapsulate a request as an object, thereby letting you queue or log request. Commands tell us to create an object for an operation and give it a method to execute. To illustrate the evolution of JUnit, we use diagrams that show snapshot of the architecture. Because we expect this class to be reused through inheritance, we declare it a public abstract. For now, ignore the fact that it implements the test interface. For the purpose of our current design here, you can think of test case as a long class. For every test case is created with a name, so it test fails, you can identify which test fails. The notion we use is simple. It annotates classes with shaded boxes containing the associated pattern. When the role of the class is in the pattern, it is obvious, then only the pattern name is shown. If the role isn't clear, then the shaded boxes are augmented by the name of the particular participant this class responded to. This notation minimizes the clutter in diagram and was first shown in here. This shows this notation applied to here to test case. blanks to fill in and run. The next problem to solve is giving the developer convenient place to put their fixture code and their test code. The declaration of test case as an abstract says that the developer is expected to reuse the test class by subclassing. However, if all we could do was to provide the superclass with one variable and no behavior, we wouldn't be doing much to satisfy our first goal, making test easier to write. Fortunately, there is a common structure to all tests. They set up a test fixture, run some code against the fixture, check some results, and then clean up the fixture. This means that each test will run with a fresh fixture, and the results of one test can't influence the result of another. This supports the goal of maximizing the value of the tests. Template method addresses our problem quite nicely. Quoting from the intent, define the skeleton of an algorithm in an operation, differing some steps to subclasses. Template method lets subclass redefine certain step to an algorithm without changing the algorithm's structure. This exactly right. We want the developer to be able to separately consider how to write the fixture, set up and tear down code, and how to write the testing code. The execution of this sequence, however, will remain the same for all tests, no matter how the fixture code is written or how the testing code is written. The default implementation of these methods do nothing. Since setup and tear down are intended to be overridden but will be called by the framework, we declare them as protected. The second snapshot, here you can see the template method here. The template, reporting test result. If the test case runs in a forecast, does anyone care about the result? Sure, you run the test to make sure they run. After the test has run, you want a record, a summary of what did and what didn't work. If test had equal chances of succeeding or failing, or if we only ever ran the one test, we could just set a flag in the test case object and go look at the flag when the test completed. However, tests are intended to be highly asymmetric. They usually work. Therefore, we only want to record the failures and a highly condensed summary of the success. The Smalltalk best practice patterns has a pattern that is applicable. It is called collecting parameter. It suggests that when you need to collect results over several methods, you should add a parameter to the method and pass an object that will collect the result for you. We create a new object, test result, to collect the result of running test. This simple version of test result only counts the number of tests run. To use it, we have to add a parameter to the test case.run method and notify the test result that the test is running. And the test result has to keep track of the number of tests to run. We declare the test result method start test as synchronized so that the single test run can collect the result safely when the tests are run in a different threads. Finally, we want to retain the simple external interface of test case. So we create a no parameter version of run that create its own test result. If tests always run correctly, then we wouldn't have to write them. Tests are interesting when they fail, especially if we didn't expect them to fail. What's more, tests can fail in ways that we expect. For example, by computing an incorrect result, or they can fail in more spectacular ways. For example, by writing outside of bound of an array. No matter how the test fails, we want to execute the follow test. JUnit distinguishes from failures and errors. Possibility of a failure is anticipated and checked for with assertions. Errors are anticipated problems like an array index out of bound exception. Failures are signals with an assertion failed error to distinguish and yeah. JUnit comes with a different implementation of test result. The default implementation counts the number of failures and errors and collects the results. The text result collects the results and present them in a textual form. Finally, the UI test result is used by the graphical version of JUnit test runner to update the graphical test status. The test results is an extension point of the framework. Client can define their own custom test classes. For example, an HTML test result reports the result as an HTML document. Now to subclasses test case again. We have applied command to represent a test. Command relies on a single method like execute called run in the test case to invoke it. The simple interface allows us to invoke different implementation of a command through the same interface. We need an interface to generally run our test. However, all test cases are implemented as a different method in the same class. This avoids the unnecessary proliferation of classes. A given test class may implement many different methods, each defining a single test case. Each test case has a descriptive name like test money equals or test money add. The test cases don't conform to a simple command interface. Different instances of the same command class need to be invoked with a different method. Therefore, our next problem is to make all test cases look the same from the point of view of the invoker of the test. Reviewing the problems addressed by the available design patterns, the adapter pattern springs to mind. Adapter has the following intent: convert the interface of the class into another interface clients expect. This sounds like a good match. Adapter tells us different ways to do this. One of them is a class adapter, which uses subclassing to adapt the interface. For example, to add test money equals to run test. We implement the subclass of money test and override the run test to invoke test money equals. To use the subclassing requires us to implement the subclass for each test case. We put an additional burden on the tester. This is against the JUnit goal that the framework should make it as simple as possible to add the test case. In addition, creating a subclass for each testing method results a class bloat. Many classes with only a single method are not worth their cost, and it will be difficult to come up with meaningful names. Java provides anonymous inner classes, which provide an interesting Java-specific solution to the class naming problem. With anonymous inner classes, we can create an adapter without having to invent a class name. This is much more convenient than full subclassing. It prevents compile time type checking that at the cost of burden on the developer. Smalltalk best practice patterns describe another solution for the problem of different instances having differently under common heading or pluggable behavior. This idea is to use a single class which can be parameterized to perform single different logic without requiring subclassing. The simple form of pluggable behavior is the pluggable selector. Pluggable selector stores a Smalltalk method selector in an instance variable. This idea is to limit is not limited to Smalltalk. This is also applicable to Java. In Java, there is no notion of method selector. However, the Java reflection API allows us to invoke a method from a string representing method name. We can use this feature to implement a pluggable selector in Java. As an aside, we usually don't use reflection in ordinary application code. In our case, we are dealing with an infrastructure framework, and it is therefore okay to wear the reflection hat. JUnit offers the client the choice of using pluggable selector or implementing an anonymous adapter class. To do so, we provide the pluggable selector as an default implementation of a run method, run test method. In this case, the name of the test case has to correspond to the name of the test method. We use reflection to invoke the method, and first we look up the method object. Once we have the method object, we can invoke it and pass it to argument. JDK 1.1 reflection API only allows us to find public method. For this reason, you have to declare test methods as public, otherwise you will get no such method exception. Don't care about one or many test suite. To get confidence in the state of a system, we need to run many tests. Up to this point, JUnit can run a single test case and report the result in a test result. Our next challenge is to extend it so that it can run many different tests. This problem can be solved easily when the invoker of the test doesn't have to care about whether it runs one or many test cases. The popular pattern to pull out in such situation is composite. To quote this intent, composite objects into a tree structure to represent part, whole hierarchies. Composite lets client treat individual objects and compositions of object uniformly. The point about part whole hierarchies is of interest here. We want to support suits of test. Composite introduces the following participant component, declares the interface we want to use to interact with our tests. Composite implements this interface and maintains the collection of tests. Leaf represent test case in a composition that conforms to the component interface. The pattern tells us to introduce an abstract class which defines the common interface for a single and composite object. The primary purpose of the class is to define an interface. When applying composite in Java, we prefer to define an interface, not an abstract class. Using an interface, avoid committing JUnit to a specific base class for tests. To all that is required is that the test conform to this interface. Test case corresponds to a leaf in a composite and implements the interface as we have seen above here. Next, we introduce the composite participant. We name this class test suite. A test suite keeps its child test in a vector. The run method delegates to its children. Finally, the client have to be able to add test to the to a suite. They can do so with the method add test. Notice how all of the these things only depends on the test interface. Since both test case and test suite conforms to the test interface, we can recursively compose suites of test suites. All developers can create their own test suites. We can run them all by creating test suites composed of those suites. This works fine, but requires to add all the tests to a suite manually. Early adapters of JUnit told us this was stupid. However, you can write a new test case. You have to remember to add it to a static suit method. Otherwise, it will not be run. We added a convenient constructor to test suit which make the test case class as an argument. Its purpose is to extract the test methods and create a suit containing them. Test methods must follow the simple conventions. They start with the prefix test and take no arguments. The convenience constructor uses this convention, constructing a test object by using reflection to find the testing method. The original way is still useful when you want to run subset of test cases only. So here we are at the end of this JUnit tour with JUnit 3.8.x. This figure shows the design of JUnit at a glance, explained with patterns here. Notice how test case, the central abstraction of in the framework, is involved in 4 patterns. The pictures of mature object design shows this same pattern density. The star of this design has a rich set of relationships with the supporting players. Here you can see the test interface here. It's a composite component here. Here you can see 2 subclasses. This test case and test suits is inherited from test. Test case has command pattern, template pattern, and composite leaf here, and pluggable selector. And test suit has a composite, and it has run method and add test method. Test suit composite of tests. Test case has run method, run test, setup, and tear down, and pluggable selector fname. Test case is connected to test result. Here it has a collecting parameter pattern, and this one is inherited from test case, and it has this class. This follows the adapter pattern. It has run test method. As an example, we can consider org.junit.vintage. It's in Marmon repository. It's the group ID here, org.junit.vintage. It's in the group JUnit-vintage. The group description is JUnit-vintage. Here you can see JUnit 3 test case. The class test case, a test case defines the fixture to run multiple tests. To define a test case, step 1, implement a subclass of test case. Step 2, define instance variables that store the state of the fixture. Step 3, initialize the fixture state by overriding setup. So it's already set up. Step 4, clean up after a test by overriding tear down method already in tear down. Each test runs in its own fixture, so there can be no side effects among test runs. For each test, implement a method which interacts with the fixture. Once the methods are defined, you can run them. The framework supports both the static type safe and more dynamic way to run a test. In a static way, you override the run test method and define the method to be invoked. The convenient way to do is with an anonymous inner class. The dynamic way uses reflection to implement run test. It dynamically finds and involves a method. In this case, the name of the test case has to correspond to the test method to be run. The test to be run can be collected into a test suite. JUnit provides different test runners which can run a test suite and collect the results. A test runner either expects a static method suite as an entry point to get a test to run, or it can extract suite automatically. Assert not null method asserts that an object isn't null. Assert false asserts that an condition is false if it isn't throws throws an assertion failed error. Assert equals here assert that two objects are equal, here expected and actual here. If they are not, an assertion failed error is thrown. A JUnit test case extend the JUnit test API class test case, and each test method must start with the word test. To run the tests in Eclipse, right click on the test class in the package explorer view and choose run as JUnit test. As an example 3, we can consider this JUnit 4 test case. The annotation type test. The test annotation tells JUnit that the public void method to which it is attached can be run as a test case. To run the method, JUnit first construct a fresh instance of the class, then invokes the annotated method. Any exception thrown by the test will be reported by JUnit as a failure. If no exceptions are thrown, the test is assumed to have succeeded. In exception testing, the parameter expected declares a test method should throw an exception. If it doesn't throw an exception, or if it throws a different exception than the one declared, the test fails. Using the parameter expected for exception testing comes with a some limitations. Only the exceptions type can be checked, and it is not possible to precisely specify the code that throws the exception. Therefore, JUnit 4 has improved its support for exception testing with assert.assertThrows class throwing runnable and the expected exception rule. With assert throws, the code that throws the exception can be precisely specified. If an exception message or one of its properties should be verified, the expected exception rule can be used. Timeout. The parameter timeout causes the test to fail if it takes longer than a specified amount of clock time measured in milliseconds. Warning: while timeout is useful to catch and terminate infinite loops, it should not be considered deterministic. Thread safety warning: test methods with timeout parameter are run in a thread other than the thread which runs a fixture ampersand before and ampersand after methods. This may yield different behavior for code that is not thread safe when compared to the same test method without timeout parameter. Consider using timeout rule instead, which ensure the test method is run on the same thread as the fixtures ampersand before and ampersand after methods. To run to your JUnit 3 or 4 test as is on the JUnit platform, simply include JUnit vintage dependency in your build and it just works. The Maven POM and Gradle build file build.gradle that are included with the same application already do this. You can run test right out of the box. In JUnit 4, a JUnit 4 test case ends with the word test. Here it is omitted here, and each test method is annotated with ampersand test. To run this test in Eclipse, right click on the test class in the package explorer view and choose run as, then JUnit test. Assert not null asserts that an object isn't null if it is an assertion error. If it is an then an assertion error is thrown. Assert false method asserts that a condition is false. If it isn't, it throws an assertion error without a message. Assert equals asserts that two longs are equals. If they are not, an assert error is thrown. This is the expected long value, and this is the actual long value. As an example 4, we can consider this Gradle segment here. The JUnit platform can run JUnit 4 base test as long as you configure test implementation dependency on JUnit 4 and test and runtime only dependency on JUnit vintage-engine implementation, similar to following here. And here org.junit.vintage. This is the group ID. As an example 5, we can consider this Maven segment. Maven Surefire and Maven failsafe can run JUnit 4 based test alongside Jupyter test as long as you configure test scoped dependencies on JUnit 4 and JUnit vintage test engine implementation similar to following. And here you can see JUnit vintage group ID. This is JUnit vintage here. As an exception example, we can consider this code segment. This is a test exception in JUnit 3. Here you can see the public string get message method. This returns the detailed message string of this throwable. Here assert equals asserts the two strings are equal here. It's expected and it's actual. As an exception, example 2, we can consider this one, test exception in JUnit 4. The class expected exception rules, the class expected exception, the expected exception rule allows you to verify that your code throws a specific exception. This is in package org.junit.rules in version JUnit 4. This is available from version 4.7. You have to add expected exception rule to your test. This is here. This doesn't affect your existing tests. After specifying the type of the expected exception, your test is successful when such an exception is thrown, and it fails if a different or no exception is thrown. This rule does not perform any special magic to make an execution continue if the exception had not been thrown. If it is nearly always a mistake for a test method to have statement after the one that is expected to throw the exception. Instead of specifying the exception type, you can characterize the expected exception based on other criteria too. The exception message contains a specific test. Here expect message and a string. The exceptions message compiles with the hamcrest matcher, expect message matcher, or the exception cause compiles with the hamcrest matcher, expect cause matcher. The exception itself compiles with the hamcrest matcher, expect matcher. You can also combine any of the presented expect methods. The test is successful if the specifications are met. It is recommended to set order of the expected exception to integer.max value if it is used together with another rule that handles the exception, for example error collector. Otherwise failing test may be successful. The assumption violated exceptions. JUnit uses assumption violated exceptions for indicating the test provide no useful information. You have to call assume method before you set expectations of the exception rule. In this case, the rule will not handle consume the exceptions, and it will handle by the framework. Now you can see here the test runner for running test in JUnit 4. JUnit is a simple open source unit testing framework tool to write and run repeatable unit tests. Also, it is an instance of the JUnit architecture for unit testing framework. It is mostly used as the unit testing tool by most developers. The main features are as below. The annotations to mark the method as the test methods, assertions for testing expected results and actual results. The test runner for running test are as shown below this picture. Here the code repository is connected to source code and unit tests. Here the source code is connected to test runner and unit test is connected to test runner. Invoke test is are connected to test runner, and test runner is connected to reports. Here you can see the different the JUnit 5 versus JUnit 4. Here the before hole instead of before class, and at after all instead of at after class, and at before each instead of at before, and at after each instead of at after, at disable instead of at ignore, at tag instead of at category, assert throws instead of expected attribute, assert timeout instead of timeout attribute. Here the annotation type before class. Sometimes several tests need to share computationally expensive setup, like logging into a database. While this can compromise the independence of test, sometimes it is a necessary optimization. Annotating a public static void no arc method with at before class causes it to be run once before any of the test method in the class. The at before class methods of super classes will be run before those of the current class, unless they are shadowed in the current class. Annotation type after class. If you allocate expensive internal resources in a before class method, you need to release them after all the tests in the class have run. Annotating a public static void method with an @after class causes that method to be run after all tests in the class have been run. All after class methods are guaranteed to run even if a before class method throws an exception. The after class methods declared in superclasses will be run after those of the current class unless they are shadowed in the current class. Annotation type before. When writing test, it's common to find several test need similar objects created before they can run. Annotating a public void method with @before causes that method to run before the test method. The @before methods of superclasses will be run before those of the current class unless they are overwritten in the current class. No other ordering is defined. If you annotation type after in org.junit, if you allocate external resources in a before method, you need to release them after the test runs. Annotating a public void method with @after classes causes that method to be run after the test method. All @after methods are guaranteed to run even if a before or test method throws an exception. @after methods declared in a superclass will be run after those of the current class unless they are overridden in the current class. Annotation type ignore. Sometimes you want to temporarily disable the test or group of tests. Method annotated with tests that are also annotated with @ignore will not be executed as tests. Also, you can annotate a class containing test method with @ignore and none of the containing test will be executed. Native JUnit 4 test runners should report the number of ignore tests along with the number of tests that ran the number of tests that failed. Annotation type category marks a test class or test method as belonging to one or more categories of test. The value of an array value is an array of arbitrary classes. This annotation is only interpreted by categories runner at present. Here you can see the annotations in JUnit 4. There are two main abstract model for JUnit framework. One of it is the abstract of test unit. Each test unit has its own scope, name, initial state, and the way how to release the resources which are allocated during the testing time. The JUnit 4 it uses inheritance models to represent that concept. With the annotation, the framework use reflection to get the meta information of the test unit. The class has its own member, so JUnit use abstract method abstract class framework member to represent it. The class member can be classified into a field and method. JUnit uses framework field and framework method which inherit from member. Framework field maintain a private object of class field which is used in reflection. So do framework method. Here the can see the interface annotatable in doc.junit.runners.model, a model element that may have annotations. Here the framework, the class framework member type parameter t, extend framework member type parameter t. Here the class framework method represent a method on a test class to be invoked at the appropriate point in test execution. These methods are usually marked with an annotation such as at test, at before, at after, at before class, at after class, etc. Here class framework method in junit.runners.model represent a method that on a test class to be invoked at appropriate point in test execution. These methods are usually marked with an annotation such as at test, at before, at after, at before class, at after class, etc. Class test class wrap a class to be run, providing method validation, annotation, searching. Here you can see the interface annotatable. The implementing classes are framework member, test class, and there are other two implementation class, test class, and here the framework here the framework class framework framework member. Here the direct known subclasses, framework method and framework field. Here you can see an important inheritance in JUnit 4. JUnit test I started using JUnit core class. It will can run us to finish the tasks. Other important inheritance shown here. The public class all default possibilities builder, extend, runner builder will be called and try to find runners to run test classes which are written by user. Finally, block JUnit 4 class runner will be called. Here you can see the interface filterable in org.junit manipulation. The runners that allow filtering should implement this interface. Implement filter to remove tests that don't pass the filter. The interface describable in jog.junit.runner. Represent an object that can describe itself. The interface sortable in org.junit.runner.manipulation. Interface for runners that allow sorting of tests. By sorting tests based on when they last failed, most recently failed first, you can reduce the average time to the first test failing. Test sorting should not be used to cope with the order dependencies between tests. Tests that are isolated from each other are less expensive to maintain and can be run individually. Class runner. A runner runs test and notifies a run notifier of significant event as it does so. You will need to subclass runner when using run with to invoke a custom runner. When creating a custom runner, in addition to implementing the abstract method here, you must provide the constructor that takes an argument the class contained in the test. The class parent runner type parameter t provides most of the functionality specific to the runner that implements the parent node in the test tree with children defined by object of same data type t. For block JUnit for class runner, t is method, and for suit t is class. Subclasses must implement finding the children of the node, describing each child and running each child. Parent runner will filter and sort children, handle at before class, at after class method, handle annotated class rules, create composite description, and run children sequentially. The class block JUnit for class runner in org.junit.runners implements the JUnit for standard test case class model as defined by the annotations in the org.junit package. Many users will never notice this class. It is now the default test class runner, but it should have exactly the same behavior as the old test runner, JUnit for class runner. The class JUnit4 aliases the current default JUnit4 class runner. For future proofing, the future versions of JUnit change the default runner class. They will also change the definition of this class. Developers wanting to explicitly tag a class as a JUnit4 class should run with junit4.class, not for example in JUnit 4.5. The class block JUnit for class runner with parameters in org.junit.runners.parameterize. A block class for class runner with parameters support. Parameters can be injected via constructor or an annotated fields. The class suit in org.junit.runners. Using suit as a runner allows you to manually build a suit containing tests from many classes. It is the JUnit4 equivalent of the JUnit 3.8.x static test suit method. To use it, annotate the class with @ run with suit.class, and at suit classes test class 1.class etc. When you run this class, it will run all the test in all the suit cases. Class parameterize in org.junit.runners. The custom runner parameterize implements parameterized tests. When running parameterized test class, instances are created for each cross product of the test method and the test data elements. Here the parent runner implemented the interface, the implemented interfaces are here filterable and sortable. And the superclass is runner, and runner implements desirable interface. Parent runner has subclasses block JUnit4 class runner and suit. Block JUnit4 class runner has subclasses JUnit4 and block JUnit4 class runner with parameters, and suit has subclass parameterize. Here you can see the life cycle of JUnit4. Here the before class, an annotated public static void no argument method will be executed before execution of any test method in the class. At after class, an annotated public static void no argument method will be executed after all test methods of this class are executed. At before, this method will be called before each test method in the class. At after, this method will be called after each test method in the class. The annotation type before class. Sometimes several tests need to share computationally expensive setup like logging into database. While this can compromise the independence of tests, sometimes it is necessary optimization. Annotating a public static void no arg method with at before class causes it to be run once before any test method in the class. The at before class method of superclasses will be run before those of the current class unless they are shadowed in the current class. Annotation type before. When writing tests, it is common to find that several tests need similar objects created before they can run. Annotating a public void method with the before at before causes that method to run before the test method. The at before method of superclasses will be run before those of the current class. Unless they are overridden in the current class, no other ordering is defined. The annotation type test. The test annotation tells JUnit that the public void method to which it is attached can be run as a test case. To run the method, JUnit first constructs a fresh instance of the test class, then invokes the annotated method. Any exceptions thrown by the test will be reported by JUnit as a failure. If no exceptions are thrown, the test is assumed to have been succeeded. Have succeeded. The annotation type after, if you allocate external resources in a before method, you need to release them after the test runs. And annotating a public void method with after causes that method to be run after test method. At after method are guaranteed to run even if at before or test method throws an exception. At after methods declared in superclasses will be run after those of the current class unless they are overridden in the current class. Annotation type after class. If you allocate expensive external resources in a before class method, you need to release them after all tests in the class have run. Annotating a public static void method with at after causes that method to be run after all the tests in the class have been run. All at after class method are guaranteed to run even if a before class method throws an exception. The at after class method declared in superclasses will be run after those of the current class unless they are shadowed in the current class. Here you can see the test class lifecycle. Start is connected to at before class. At before class is connected to here the for each and here for each at test case. Here you can see the at before and then at test, and after that then at after. Then it's connected to at after class and then end. Now we are focusing on JUnit 4.12. As an example, we can consider this code segment. Here the annotation type test. The test annotation tells JUnit that the public void method to which it is attached can be run as a test case. To run the method, JUnit first construct a fresh instance of the class, then invokes the annotated method. Any exceptions thrown by the test will be reported by JUnit as a failure. If no exceptions are thrown, the test is assumed to have succeeded. This is in the package package org.junit. As an example 2, we can consider this Maven segment. Maven Surefire and Maven failsafe can run JUnit 4 based test alongside Jupyter tests as long as you configure test scope dependencies on JUnit 4 and the JUnit vintage-engine implementation similar to following here. And you can see here JUnit 4 and the scope test. Now we are considering here the annotation interface type. Enable JUnit for migration support in package org.junit.jupiter.migration support in modules org.junit.jupiter.migration support. Enable JUnit for migration support is a class level annotation that enables all JUnit for migration support within JUnit Jupyter. I included this here basically for the annotation, but this is in the JUnit org.junit.jupiter. Now we are considering category support in running JUnit 4 test on the JUnit platform in migrating from JUnit 4 for test classes or methods that are annotated with at category. The junit-vintage-test-engine exposes the category fully qualified class name as a tag for the corresponding test class or test method. For example, if a test method is annotated with, like here, the category here example.class, it will be tagged with here com.seme.example. Similar to the categories runner in JUnit 4, this information can be used to filter the discovered test before executing them. Now we are considering migration tips. The following are the topics that you should be aware of when migrating existing JUnit 4 test to JUnit Jupiter. Annotations reside in the org.junit.jupiter.api package. Assertions reside in org.junit.jupiter.api.assertions. Note that you may continue to use the assertion method from org.junit.assert or any other assertions library such as assert j, hamcrest, truth, etc. Assumptions reside in org.junit.jupiter.api.assumptions. Note that the Jupiter 4.5.4 and other versions support method from JUnit 4's org.junit.assume class for assumptions. Specifically, JUnit Jupiter supports JUnit 4's assumption violated exception to signal that the test should be aborted instead of marked as failure. At before and at after no longer exist, used at before each, at after each instead. At before class and at after class no longer exist, used at before all and at after all instead. Ignore no longer exist, used at disabled or one of the other built-in execution condition instead. At category no longer exist, use at tag instead. At run with no longer exist, superseded by at extend with. At rule and at class rule no longer exist, superseded by at extend with and at register extension. At test expected equal etc. And the expected exception rule no longer exist. Use assertions dot assert throws instead. Assertions and assumptions in JUnit Jupiter accept the failure message as their last argument instead of the first one. Now we are considering JUnit for rule support. This limited form of rule support can be switched on by the class level annotation at enable rule migration support. the annotation interface at enable rule migration support in package junit-jupiter.migration support.rules in module junit-jupiter.migration support rules. This annotation is in Jupyter. As stated before, the JUnit-Jupyter does not and will not support JUnit 4 rules natively. The JUnit team realizes, however, that many organizations, especially large ones, are like to have large JUnit 4 codes bases that makes use of custom rules. To serve these organizations and enable a gradual migration path, the JUnit team has decided to support the selection of JUnit 4 rules verbatim within JUnit-Jupyter. The support is based on adapter and is adapters and is limited to those rules that are semantically compatible to JUnit Jupyter extension model. That is, those do not have completely changed the overall execution flow of the test. The JUnit Jupyter migration support module from the JUnit Jupyter currently support the following 3 rule types, including subclasses of these types: org.junit.rules.external resource, including org.junit.rules.temporary folder, org.junit.rules.verify, including org.junit.rules.error collector, org.junit.rules.expected exception. As in JUnit 4, rule annotated fields as well as methods are supported. By using these class level extensions on the test class, such rule implementation in legacy code bases can be left unchanged, including JUnit 4 rule import statement. This limited form of rule support can be switched on by the class level annotation at enable rule migration support. This annotation is composed annotation which enable all rule migration support extensions, verifier support, external resource support, and expected exception support. You may alternatively choose to annotate your test class with at enable JUnit 4 migration support, which registers migration support for rules and JUnit 4's at ignore annotation. However, if you intend to develop a new extension for JUnit Jupyter, please use the new extension model of JUnit Jupyter instead of rule-based model of JUnit 4. Now we are considering JUnit 4 at ignore support. The ignore condition is an execution condition that disables test classes or test method that are annotated with at ignore. In order to provide a smooth migration path from JUnit 4 to JUnit Jupyter, the JUnit Jupyter migration support module provides support for JUnit 4's at ignore annotation, analogous to Jupyter's at disable annotation. To use at ignore with JUnit Jupyter based test, configure the test dependency on the JUnit Jupyter migration support module in your build, and then annotate your class with extend with ignore condition class. So enable JUnit 4 migration support, which automatically registers the ignore condition along with limited JUnit 4 rule support. The ignore condition is an execution condition that disables the test classes or test method that are annotated with at ignore. Now we are considering failure message argument. The method affected by this change are as follows. The assumptions and assertions classes in junit-jupiter declare argument in a different order than in junit 4. In junit 4, assertion and assumption method accept the failure message as first argument, whereas in junit-jupiter, assertion and assumption method accept the failure message as the last argument. For instance, the method assert equals in junit 4 declared as assert equals string message object expected object actual, but in junit-jupiter is declared as assert equal object expected object actual string message. The rationale for this is that failure message is optional and optional argument should be declared after required arguments in the method signature. The method affected by this change are the following: assertions, assert true, assert false, assert null, assert not null, assert equals, assert not equals, assert array equal, assert same, assert not same, assert throws. Assumption: assume true, assume false. Test annotation supports two optional parameters for exception testing and for limiting test execution time. Here we are considering expected parameter for as an exception example here. The parameter expected declares that the test method should throw an exception. If it does not throw an exception, or if it throws a different exception than the one declared, the test fails. For example, this test succeeds here. Using the parameter expected for exception testing comes with some limitations. Only the exceptions type can be checked, and it is not possible to precisely specify the code that throws the exception. Therefore, junit 4 has improved its support for exception testing with assert throws class throwing runnable and the expected exception rule. With assert throws, the code that throws the exception can be precisely specified. If the exception's message or one of its properties should be verified, the expected exception rule can be used. As an error example, we can consider this one occurred in Android Studio, failed to resolve JUnit 4.12. Now we are focusing on junit-vintage-engine. junit-vintage-test-engine implementation that allows one to run vintage JUnit test on the JUnit platform. Vintage test includes those written using JUnit 3 or JUnit 4 APIs, or test written using testing frameworks built on those APIs. Core package for the JUnit vintage test engine. Here you can see the dependency diagram. Here you can see JUnit vintage engine in org.junit.vintage package. As an example, we can consider the module org.junit.vintage.engine. Provides a test engine for running JUnit 3 and 4 based test on the platform. As an example 2, we can consider org.junit.vintage.engine package, core package for the JUnit vintage test engine. See, this is in module org.junit.vintage.engine. As an example 3, we can consider vintage test engine. the class vintage test engine, the JUnit vintage test engine. This is available since version 4.12, and this is in the module org.junit.vintage.engine and in the package the org.junit.vintage.engine. As an example we can consider this Gradle segment. The JUnit platform can run JUnit 4 base test as long as you configure test implementation dependency on JUnit 4 and test runtime only dependency on JUnit vintage test engine. Implementation similar to following, and here you can see artifact JUnit vintage engine. This is the module JUnit vintage engine of JUnit 5. This is in the group ID org.junit.vintage. As an example 5, we can consider this Maven segment. Maven Surefire and Maven failsafe can run JUnit 4 base test alongside Jupyter test as long as you configure test scope dependencies on JUnit 4 and the JUnit vintage test engine implementation similar to following here. And here you can see artifact JUnit artifact ID JUnit vintage engine here, the module JUnit vintage engine of JUnit 5 is in the group ID org.junit.vintage. Now we are considering additional Gradle dependencies in IntelliJ IDEA in IDE support in running test. Here the artifact JUnit vintage engine in group ID org.junit.vintage, a thin layer on top of JUnit 4 to allow running vintage tests based on the JUnit 3.8 and JUnit 4 with the junit-platform-launcher infrastructure. Here you can see additional Maven dependencies. Now we are considering JUnit test engines in advanced topics. JUnit vintage engine, a thin layer on top of JUnit 4 to allow running vintage test based on JUnit 3.8 and JUnit 4 with the junit-platform-launcher infrastructure. Now we are considering JUnit vintage in dependency metadata. The artifact ID JUnit vintage engine in version here, for example 5.10.0 in group ID org.vintage org.junit.vintage. The JUnit Vintage test engine implementation that allows one to run vintage JUnit test on the JUnit platform. Vintage tests include those written using JUnit 3 or JUnit 4 APIs, or test written using testing framework built on those APIs. As an exception example, we can consider this one, internal record and org.junit.platform.commons.junit exception test engine with ID JUnit vintage failed to discover test, etc. As an error example, we can consider this java.lang.no such method error org.junit-vintage-engine.descriptor.runner test description get all descendants. As an error example 2, we can consider this error occurred in Spring Boot 2.2 and JUnit 5 environment. Failed to execute goal org.apache.maven.plugins.maven file sure plugin plugin 2.22.2 test default test on project xxx. There are test failures and etc. Then here please refer to the project workspace xxx target file surefire reports the individual test results. Please refer to the dump files if any exist. There was an error in the forked process test engine with ID JUnit vintage failed to discover test, etc. Now we are focusing on new test JUnit 5. New tests JUnit 5. Here you can see the default execution mode configuration combinations. By default, JUnit Jupyter tests are run sequentially in a single thread. Running tests in parallel, for example, to speed up the execution, is available as an opt-in feature since version 5.3. To enable parallel execution, set the junit.jupiter.execution.parallel.enable configuration parameter to true. For example, the junit-platform-properties. Please note that enabling this property is only the first step to required to execute test in parallel. If enabled, test classes and methods will still be executed sequentially by default. Whether or not a node in the test tree is executed concurrently is controlled by its execution mode. The following two modes are available. Same thread, force execution in the same thread used by the parent. For example, when used on a test method, the test method will be executed in the same thread as any at before all or at after all methods of the containing test class. Concurrent, execute concurrently unless a resource lock forces execution in the same thread. By default, the nodes in this test tree use the same thread execution mode. You can change the default by setting the junit.jupiter.execution.parallel.mod.default configuration parameter. Alternatively, you can use the @execution annotation to change the execution mode for annotated elements and its sub-element, if any, which allows you to activate parallel execution for individual test classes one by one. Configuration parameters to execute all tests in parallel. junit.jupiter.execution.parallel.enabled equal true. junit.jupiter.execution.parallel.mod.default equal concurrent. The default execution mode is applied to all nodes of the test tree with a few notable exceptions, namely test classes that use the lifecycle.per-class mode or method order, except for method order.random. In the former case, the test authors have to ensure that the test class is thread safe. In the latter, concurrent execution might conflict with the configured execution order. Thus, in both cases, test methods in such test classes are only executed concurrently if the at execution concurrent notation is passed on the test class or method. When parallel execution is enabled and the default class order is registered, the top level test classes will initially be sorted accordingly and scheduled in that order. However, they are not guaranteed to be started in exactly that order, since the threads they are executed on are not controlled directly by JUnit. All nodes of the test tree that are configured with the concurrent execution mode will be executed fully in parallel according to the provided configuration while observing the declarative synchronization mechanism. Please note that the capturing standard output or error needs to be enabled separately. In addition, you can configure the default execution mode for a top level classes by setting junit.jupiter.execution.parallel.mod.class.default configuration parameter. By combining both configuration parameters, you can configure classes to run in parallel, but there are methods in the same thread. Configuration parameters to execute top level classes in parallel, but methods in the same thread. junit.jupiter.execution.parallel.enabled equal true and junit.jupiter.execution.parallel.mod.default equal same underscore thread, and junit.jupiter.execution.parallel.mod.classes.default equal concurrent. The opposite combination will run all methods within one class in parallel, but top level class will run sequentially. Configuration parameter execute top level classes sequentially, but there are methods in parallel. junit.jupiter.execution.parallel.enabled equal true, junit.jupiter.execution.parallel.mod.default equal concurrent, and junit.jupiter.execution.parallel.mod.classes.default equal same underscore thread. The following this diagram illustrates how execution of two top level test classes A and B with two test methods per class behaves for all four combinations of junit.jupiter.execution.parallel.mod.default and junit.jupiter.execution.parallel.mod.classes.default. See labels in the first column. The default execution mode configuration combinations, if the junit.jupiter.execution.parallel.mod.classes.default configuration parameters not explicitly set, the value for junit.jupiter.execution.parallel.mod.default will be used instead. Here the same thread and same thread. Here the a.test1, then a.test2, b.test2, then a.test1, b.test1, then b.test2. Here the same thread concurrent. Here the a.test1, and here the top level classes. Execute the top level classes in parallel, but their method in the same thread. Here the to execute top level classes sequentially, but there are methods in parallel. Here classes and methods are in parallel here. As an example, we can consider this code segment. Here you can see annotation interface test. Test is used to signal that the annotated method is a test method, and at test method must not be private or static and must not return a value. Ampersand test methods may optionally declare parameters to be resolved by parameter resolvers. Ampersand test may also be used as a meta annotation in order to create a custom composed annotation that inherits the semantics of ampersand test. The annotation interface disabled here. Disabled is used to signal that the annotated test class or test method is currently disabled and should not be executed. Ampersand disabled may optionally be declared with a reason to document why the annotated test class or test method is disabled. This one, when applied at the class level, all test methods within that class are automatically disabled as well. When applied at the method level, the presence of this annotation does not prevent the test class from being instantiated. Rather, it prevents the execution of the test method and method level lifecycle callbacks, such as ampersand before each method, ampersand after each methods, and corresponding extension APIs. This is modify the reason this annotation test class or test method is disabled here. These annotations are in the module org.junit-jupiter-api and in the package org.junit-jupiter-api. As an example, we can consider this code segment here. Public static t_extend throwable t assert throws class t executable. Assert that the execution of supplied executable throws an exception of the expected type and return the exception. If no exception is thrown, or if an exception of a different type is thrown, this method will fail. If you do not want to perform additional checks on the exception instance, ignore the return value. here this is the expected type and this is the executable. Here here in assert equals assert that the expected and actual are equal. If both are null, they are considered equal. Here and this is the expected and this is the actual. These methods are in class assertions. As an error example, we can consider this code segment. This error occurred in the environment JUnit 5, Java 9 and Eclipse Oxygen 1.8. Java.lang.class no class def found error. Org JUnit-platform-launcher core launcher factory, then etc. Now we are focusing on Jupyter. JUnit-Jupyter is the combination of the new programming model and extension model for writing tests and extensions in JUnit 5. The Jupyter subproject provides a test engine for running Jupyter-based tests on the platform. Here in dependency diagram, you can see org.junit.jupyter package, and you can see here junit-jupiter-engine and junit-jupiter migration support, junit-jupiter params, and this is junit-jupiter, and here junit-jupiter-api. Here you can see per method lifecycle. With regarding lifecycle methods, a lifecycle method is any method that is annotated with before all, after all, before each, and or after each annotation. The lifecycle methods execute before or after executing the actual test methods. Before all and after all annotations denote that the annotated method should be executed before or after all test methods in the test class. If you have 10 test methods in the test class, before each and after each will be executed 10 times, but before each and after each here, but before all and after all only once. Here you can see a per method lifecycle. In per method lifecycle, this is a test instance lifecycle here. By default, JUnit creates a new instance of the test class before executing each test. Each test method. This helps us to run individual test methods in isolation and avoid unexpected side effects. Here this before all and after all are static methods normally. This is because when creating a new test instance per test method, there is no shared state otherwise. When you're looking at the output, we can see that JUnit construct the test class once per each test. Each test method. The lifecycle methods for entire fixture have been executed once, and the lifecycle methods for tests have been executed multiple times. Here the annotation interface before all, ampersand before all is used to signal that the annotated method should be executed before all tests in the current test class. In contrast to ampersand before each, methods before all methods are only executed once for a given test class. Annotation interface before each, ampersand before each is used to signal that the annotated method should be executed before each ampersand test or repeated test or ampersand parameterized test or ampersand test factory and ampersand test template method in the current test class. Annotation interface after each, ampersand after each is used to signal that the annotated method should be executed after each ampersand test, ampersand repeated test, ampersand parameterized test, ampersand test factory, and ampersand test template method in the current test class. Annotation interface after all, ampersand after all is used to signal that the annotated method should be executed after all tests in the current test class. In contrast to ampersand after each methods, after all methods are only executed once for a given test class. Here before all is connected to constructor test class instance, and constructor test class instance is connected to before each, ampersand before each, and ampersand before each is connected to execute test. Execute test is connected to ampersand after each. Ampersand after is connected to construct a test class instance. Next test is passed from after each to construct a test class instance. After each, ampersand after is connected to ampersand after all test done is passed from ampersand after each to ampersand after all. Here you can see test see a per class lifecycle or test instance per class. It is also possible to make JUnit execute all test method in the same test instance. If we annotate the test class with ampersand test instance lifecycle.per class, JUnit will create a new test instance once per test class. So because of the shared instance, there is now no need for the method to be static. From the execution results, we can see that the execution order of the lifecycle methods has not changed. However, the difference is that JUnit constructs the test class only once. The fundamental difference is that the default lifecycle method constructing a new test class instance resets the state stored in the instance variable, when per class lifecycle method construct the instance only once. State stored in instance variable is shared between tests. If your test methods rely on state stored in instance variable, you may need to reset the state in before each and or after each lifecycle methods. Try to avoid writing tests that rely on state stored in instance variables. Here you can see the construct a test class instance is connected to assigned before all, and before is connected to before each, and before each is connected to execute test, and execute test is connected to after each, after is connected to before each, and new test is passed from after each to before each, and after is connected to after all, and all test done is passed from after each to after all. Here you can see extension lifecycle. junit-Jupiter provides extension authors callbacks that can be used to tap into the lifecycle events of tests. The extension model provides several interfaces for extending test at various points in the extension lifecycle. Extension authors are free to implement all or some of these lifecycle interfaces. Interface before all callback. Before all callback defines the API for extensions that wish to provide additional behavior to test containers once before all tests in the container have been executed. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to test before an individual test and any user-defined setup methods. For example, ampersand before each methods. For that, the tests have been executed. Interface before test execution callback. Before test execution callback defines the API for extensions that wish to provide additional behavior to test immediately before an individual test is executed, but after any user-defined setup methods. For example, ampersand before each methods have been executed for that test. Interface after test execution callback. After test execution callback defines the API for extensions that wish to provide additional behavior to test immediately after an individual test has been executed, but before any user-defined teardown methods. For example, ampersand after each methods have been executed for that tests. Interface after each callback. After each callback defines the API for extensions that wish to provide additional behavior to tests after an individual test and any user-defined teardown methods. Ampersand after each methods for that test have been executed. Interface after all callback. After all callbacks defines the API for extensions that wish to provide additional behavior to test containers once after all tests in the container has been executed. Here you can see the lifecycle callbacks here. Before all callback is connected to before each callbacks, and before each callbacks is connected to before test execution callback. Before test execution callback is connected to after test execution callback. After test execution callback is connected to after each callback. After each callback is connected to after all callback. Here you can see the junit architecture, basically considering junit-Jupiter. One could think that junit is solely a testing framework, and that while this is theoretically right, Junit is actually composed of three modules: junit-platform, junit-Jupiter, and junit-vintage. Junit-platform, the platform module is essential module that runs the test on JVM. The junit-jupiter, the Jupyter module provides programmers a new combination of the programming model and execution for writing tests on JUnit 5. JUnit Vintage, the Vintage module allows running tests from older versions, the JUnit 3 and JUnit 4 on the platform. Here you can see as an example is connected to junit-jupiter. Here Jupyter is connected to junit-jupiter-param, junit-jupiter-api, junit-jupiter-engine, and junit-jupiter-param is connected to junit-jupiter-api, and junit-jupiter-engine is connected to junit-jupiter-api. Junit-jupiter-param is connected to API Guardian API. And here junit-jupiter API is connected to API Guardian API, junit-platform commons, and open test 4j. Here junit-jupiter-engine is connected to API Guardian API and junit-platform-engine. Here the junit-platform-engine is connected to API Guardian API and junit-platform commands and open test 4j. And here junit-platform commands is connected to API Guardian API. Here the junit-jupiter aggregates artifact that transitively pulls in dependencies on junit-jupiter API, junit-jupiter-params, and junit-jupiter-engine for simplified dependency management on inbuilt tools such as Gradle and Maven. Junit-Jupiter-API, Junit-Jupiter-API for writing tests and extensions. Junit-Jupiter params supports for parameterized test in Junit-Jupiter. Junit-Jupiter-engine, Junit-Jupiter test engine implementation only required at runtime. Here the this is published in at API Guardian jar, and in addition, here the most of the artifacts have a direct and transitive dependency on the following open test 4j jar. Junit platform commons, common APIs and support utilities for JUnit platform. Any API annotated with at API status equal internal is intended to solely for usage within the JUnit framework itself. Any usage of internal APIs by external parties are not supported. JUnit platform-engine, public APIs for test engines. As an example, we can consider junit-jupiter-params. The artifact ID junit-jupiter-params support for parameterized tests in junit-jupiter. This is in the group ID org.junit.jupiter. As an example, too, we can consider this code segment. Following example demonstrates a parameterized test that uses ampersand value source annotation to specify a string array as the source of arguments. Annotation interface parameterized test. Ampersand parameterized test is used to signal that the annotated method is a parameterized test method. Such methods must not be private or static. Parameterized tests make it possible to run a test multiple times with different arguments. They are declared just like a regular ampersand test method, but use ampersand parameterized test annotation instead. In addition, you must declare at least one source that will provide the argument for each invocation, and then consume the arguments in the test method. When executing this parameterized test method, each invocation will be reported separately. For instance, the console launcher will print output similar to the following here. As an example 3, we can consider JUnit artifact ID junit-jupiter-migration support. Support for migrating from JUnit 4 to JUnit Jupiter, only required for support for JUnit 4's ampersand ignore annotation and for running selected JUnit 4 rules. This is in group ID org.junit.jupiter. Here, as an example 4, we can consider this code segment. Annotation interface enable JUnit 4 migration support. Enable JUnit 4 migration support is a class level annotation that enables all JUnit 4 migration support within JUnit Jupiter. Specifically, this annotation registers all extensions supported by ampersand enable rule management rule migration support, and provides support for JUnit's force ampersand ignore annotation for disabling test classes and test methods. Technically speaking, ampersand enable JUnit for migration support is a composed annotation which registers all of the following migration extensions: verifier support, external resource support, expected exception support, and ignore condition. Note, however, that you can optionally register one or more of these extensions explicitly without the use of this composed annotation. And this is in module org.junit.jupiter.migration support, and in the package org.junit.jupiter.migration support. In order to provide the smooth migration path from JUnit 4 to JUnit Jupiter, the JUnit-Jupiter-migration support module provides support for JUnit 4's ignore ampersand ignore annotation analogous to Jupiter's ampersand disabled annotation. To use ampersand ignore with JUnit Jupiter based test, configure a test dependency on the JUnit-jupiter-migration support module in your build, and then annotate your test class with extent with ignore condition.class, or enable enable JUnit for migration support, which automatically registers the ignore condition along with limited JUnit for rule support. The ignore condition is an execution condition that disable test class or test methods that are annotated with ignore. As an example 5, we can consider this Gradle segment. To configure support for JUnit Jupyter based test, configure a test implementation dependency on the dependency aggregating JUnit Jupyter artifact, similar to the following here. And here you can see the group ID org.junit.jupyter, JUnit Jupyter here. As an example 6, we can consider this one, the Maven segment here. To configure the support for JUnit Jupyter based tests, configure test scoped dependencies on the JUnit Jupyter API and the JUnit Jupyter test engine. Implementation similar to following here. You can see here group ID org.junit.jupyter, JUnit Jupyter here. Here, as an example 7, we can consider per method lifecycle here in this code segment. A lifecycle method is we are considering lifecycle methods also. A lifecycle method is any method that is annotated with sign before all, sign before after all, sign before each, sign after each annotation. Lifecycle methods execute before or after executing the actual test methods. The ampersand before all and ampersand after all annotations denote that the annotated method should be executed before or after all test methods in the test class. Respectively, ampersand before each and ampersand after each means that annotated method should be executed before and after each test method in the test class. If you have 10 methods, 10 test methods in the test class, before each and after each will be executed 10 times, but before all and after all only once. By default, JUnit creates an here per method lifecycle. By default, JUnit creates a new instance of the test class before executing each test. This helps us to run individual test methods in isolation and avoids unexpected side effects. Notice how the methods annotated with ampersand before all, ampersand after all are static methods. This is because when creating a new test instance per test method, there is no shared state otherwise. Executing the test in the test class gives us the following output. Actually, the output has been formatted to make it more obvious. Looking at the output, we can see that JUnit constructs the test class once per each test. Test method, the lifecycle method for an entire fixture has been executed once. And the lifecycle method for test have been executed multiple times. Here, annotation interface before all. Ampersand before all is used to signal that the annotated method should be executed before all tests in the current test class. In contrast to ampersand before each methods, ampersand before all methods are only executed once for a given test class. Annotation interface after all. Ampersand after all is used to signal that the annotated method should be executed after all tests in the current test class. In contrast to ampersand after each methods, after all methods are only executed once for a given test class. Annotation interface before each. Ampersand before each is used to signal that the annotated method should be executed before each ampersand test, repeated test, ampersand parameterized test, ampersand factory, and ampersand test template methods in the current test class. Annotation interface after each is used to signal that the annotated method should be executed after each ampersand test, repeated test, ampersand parameterized test, ampersand test factory, and ampersand test template method in the current test class. Here the ampersand test is used to signal that annotated method is a test method, and ampersand test methods must not be private or static and must not return a value. Ampersand test method may optionally declare parameters to be resolved by parameter solvers, and ampersand test may also be used as a meta annotation in order to create custom composed annotation that inherits the semantics of ampersand test. per class lifecycle. It is also possible to make JUnit to execute all test methods on the same test instance. If we annotate the test class with ampersand and its test instance lifecycle dot per underscore class, JUnit will create a new test instance once per test class. Because of the shared instance, there's now no need for the methods to be static. Consequently, output of the test execution is now a little different. From the result, we can see that the execution order of lifecycle methods has not changed. However, the difference is that the JUnit construct a test class only once. The fundamental difference is that the default lifecycle method constructing a new test class instance and reset the state stored in the instance variable. When the per class lifecycle method construct the instance only once, state stored in the instance variables is shared between tests. If your test methods rely on the state stored in instance variable, you may need to reset the state in ampersand before each and ampersand after each lifecycle methods. Try to avoid writing tests that rely on state stored in instance variables. Extension lifecycle. When using extensions, JUnit calls extension lifecycle callbacks in addition to lifecycle methods in the test class. JUnit guarantees wrapping behavior for multiple registered extensions. Given extension 1 and extension 2, it is guaranteed the before callbacks of extension 1 execute before extension 2. Similarly, it's guaranteed by after callbacks of extension 1 execute after extension 2. Executing the example here, we can see the wrapping behavior of the extensions. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to test before an individual test, and any user-defined setup methods for example, before before each methods for that test have been executed. Concrete implementation often implement after each callback as well, if you do not wish to have your callback wrapped around user-defined setup and teardown methods. Implement before test execution callback and after test execution callback instead of before each callback and after each callback. Here you can see the method void before each extension context and this callback that is invoked before an individual test and any user-defined setup methods for that test have been executed. Interface after each callback. After each callback defines API for extensions that wish to provide additional behavior to test after an individual tests and any user-defined teardown methods, for example, after each for that test have been executed. Concrete implementation often implement before callback as well. If you do not wish to have your callback wrapped around user-defined setup and teardown method, implement before test execution callback and after test execution callback instead of before each callback and after each callback. Method void after each extension context callback that is invoked after an individual test and any user-defined teardown methods for that the test have been executed. Here annotation interface extend with. Extend with is a repeatable annotation that is used for to register extension for the annotated test class, test interface, test method, parameter field. Annotated parameters are supported in test class constructed in test methods and in before all, after all, before each, after each cycle methods. Extend with fields may be either static or non-static. As an example 10, we are considering module org.junit.jupiter aggregates all JUnit-Jupiter modules. Here JUnit-Jupiter in dependency metadata, the group ID org.junit.jupiter. Here the artifact ID JUnit-Jupiter aggregate artifact that transitively pulls in dependencies on junit-jupiter-api, junit-jupiter-params, and junit-jupiter-engine for simplified dependency management in built tools such as Gradle and Maven. junit-jupiter-api, the junit-jupiter-api for writing test and extensions. junit-jupiter-engine, junit-jupiter test engine implementation only required at runtime. junit-jupiter-params, support for parameterized tests in junit-jupiter. junit-jupiter migration support for migrating from JUnit 4 to JUnit-Jupiter, only required for support for JUnit 4's @igno annotation and for running selected JUnit 4 rules. As an error example, we can consider this one. Ampersand parameter 0 is used more than once, and java.line.exception parameter is used more than once at org.junit.runners.parameterize.block JUnit 4 test class runner with parameters.valid text field. Now we are focusing on junit-jupiter-api. junit-jupiter-api for writing tests and extensions. Here you can see the sequential workflow of the lifecycle annotations for JUnit 5 is as follows. The method 1, the method annotated with at before all, is executed once at the start of the class. To the method annotated with the before each executes before test case 1 begins. 3, the method test case 1 annotated with at test is the test case in the class. The method annotated with at after each runs after the test case 1 complete execution. 5, the method annotated with before each at before each execute before the test case 2 begins. 6, the method test case 2 annotated with that test is the test case in the class. 7, the method annotated with that after each runs after the test case 2 complete execution. 8, the method annotated with at after all is executed once at the end of the class after both test case 1 and test case 2 are executed. Here the annotation interface before all in package org.junit-jupiter-api in module org.junit-jupiter-api. At before all is used to signal that the annotated method should be executed before all test in the current test class. Annotation interface before each. At before each is used to signal that the annotated method should be executed before each at test at repeat test at parameter state at test factory and at test template method in the current test class. The annotation interface test at test is used to signal that the annotated method is the test method. Annotation interface after each. At after each is used to signal that the annotated method should be executed after each at test. At repeat test, at parameters test, at test factory and at test template method in the current test class. Annotation interface after all. At after all is used to signal that the annotated method should be executed after all tests in the current test class. Here the at before each before all is connected to at before each, and at before each connected to at test case 1. It is connected to at after each, and then at after is connected to at before each, and at before each is connected to at test case 2, and it is connected to at after each, and at after each is connected to at after all. Here you can see the relative execution order of the user code and extension code. This diagram illustrates the relative order of user supplied code. And the extension code. User supplied test and the lifecycle method are shown in orange, with callback code implemented by extensions shown in blue. The gray box denotes the execution of a single test method and will be repeated for every test method in the test class. Here the step 1, the interface or annotation. The interface org.junit-jupiter-api.extension.before all callback. Extension code executed before all tests of the container are executed. To the annotation org.junit-jupiter-api.before all user code executed before all tests of the container are executed. Interface 3, the interface org.junit-jupiter-api.extension.lifecycle method execution exception handler handler before all method execution exception. Extension for handling exception thrown from at before all methods. For interface org.junit-jupiter-api.extension.before each callback. Extension code executed before each test is executed. File the annotation org.junit-jupiter-api.before each user code executed before each test is executed. The 6, the interface org.junit-jupiter-api.extension.lifecycle method execution exception handler handler before each method execution exception. Extension code for handling exception thrown from the before each methods. 7, interface org.junit-jupiter-api.extension.before test execution callback. Extension code executed immediately before a test is executed. 8, annotation org.junit-jupiter-api.test user code of the actual test method. 9, interface org.junit-jupiter-api.extension.test execution exception handler. Extension code for handling exception thrown during a test. 10, interface org.junit-jupiter-api.extension. After test execution callback. Extension code executed immediately after a test execution and its corresponding exception handlers. 11, annotation org.junit-jupiter-api. After each user code executed after each test is executed. 12, interface org.junit-jupiter-api.extension.lifecycle method execution exception handler handle after each method execution exception. Extension code for handling exception thrown from at after each methods. 13 interface org.junit-jupiter-api after each callback. Extension code executed after each test is executed. 13 14 annotation org.junit-jupiter-api.after all. User code executed after all tests of the container are executed. 15 interface org.junit-jupiter-api.extension.lifecycle method execution exception handler handle after all method execution exception. Extension code for handling exception thrown from the after all methods. Interface org.junit.jupiter.api.extension.after all callback. Extension code executed after all tests of the container are executed. In the simplest case, only the actual test method will be executed. Step 8. All other steps are optional depending on the presence of user code or extension support for corresponding lifecycle callbacks. For further details on the various lifecycle callbacks, please consult the respective Java doc for each annotation and extension. Here the interface before all callback in package org.junit-jupiter.api.extension in module org.junit-jupiter.api. This before all callback defines and the API extension that wish to provide additional behavior to test containers once before all tests in the container have been executed. The annotation interface before all in package org.junit-jupiter.api in module org.junit-jupiter.api. At before all is used to signal that annotated method should be executed before all tests in the current test class. The here the default void handle before all method execution exception extension context throwable in the interface lifecycle method execution exception handler. Handle the supplied throwable that was thrown during the execution of at before lifecycle method. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to tests before an individual test and any user-defined setup method, for example, before each methods for that the test have been executed. Annotation interface before each. At before each is used to signal that the annotated method should be executed before each at test at repeated test, at parameterized test, at test factory, and at test template method in the current test class. Default void handle before each method execution exception, extension context throwable in interface lifecycle method execution exception handler. The handle the supply throwable that was thrown during the execution of before each lifecycle method. Interface before test execution callback. Before test execution callbacks defines the API for extension that wish to provide additional behavior to the test immediately before an individual test is executed. But after any user-defined setup method, for example, at before each methods have been executed for that test. Annotation interface test. A test is used to signal that annotated method is a test method. Interface test execution exception handler. The test execution exception handler defines the API for extensions that wish to handle exceptions thrown during the test execution. Interface after test execution callback. After test execution callbacks define the API for extensions that wish to provide additional behavior to test immediately after an individual test has been executed before any user-defined tear down methods. For example, after each methods have been executed for that test. Annotation interface after each. After each is used to signal that the annotated method should be executed after each at test, at repeated test, at parameterized test, at test factory, and at test template method in the current test class. Handle after each method execution exception. The default void handle after each method execution exception, extension context throwable in interface lifecycle method execution execution exception handle the supply throwable that was thrown during the execution of after each lifecycle method. interface after each callback. After each callback, define the API for extensions that want to provide that wish to provide additional behavior to test after an individual test, and any user-defined tear down methods, for example, at after each method that the test have been executed. The annotation interface after all. At after all methods must have a void return. The after all is used to signal that the annotated method should be executed after all tests in the current test class. The default void handle after all method execution exception, extension context throwable in interface lifecycle method execution exception handle the supply throwable that was thrown during the execution of at after all lifecycle method. Interface after all callback. After all callback, define the API for extensions that wish to provide additional behavior to test containers once after all tests container have been executed. Here the extension codes are here, the before all callback, before and these exceptions, and before each callback, before test execution callback, after test execution callback, after each callback, after all callback, and these lifecycle methods. And the user codes are at before all, at before each, at test, at after each, at after all. Here the steps, the order is before all callback, then at before all to the lifecycle method execution exception handler at hash handle before all method execution exception, then before each callback, then at before each, then lifecycle method execution exception handler at hash handler before each method execution exception, then before test execution callback, then at test, then test execution exception handler, then after test execution callback, then at after each, then lifecycle method execution exception handler hash handle after each method execution exception, then at after each callback, then at after all, then lifecycle method execution exception handler hash handle after all method execution exception, then after all callback. Example, we can consider the module org.junit-jupiter-api defines JUnit-Jupiter API for writing tests. As an example too, we can consider this code segment writing tests. The following example provide a glimpse at the minimum requirement for writing a test in JUnit-Jupiter. Annotation interface test. Ampersand test is used to signal that the annotated method is a test method. Annotation method must be must not be private or static and must not return a value. Annotation test methods may optionally declare parameters to be resolved by parameter resolvers, and annotation test may be used as a meta annotation in order to create a custom composed annotation that inherits the semantics of ampersand test. This is in the module org.junit.jupiter.api and package org.junit.jupiter.api. As an example 3, we can consider extension model. For example, to register a web service extension for a particular test method, you would annotate the test method as follows here. We assume the web server extension starts a local web server and injects the server's URL into parameters annotated with ampersand web server URL. Annotation interface extend with. Ampersand extend with is a repeatable annotation that is used to register extension for the annotated test class, test interface, test method, parameter or field. Here you can use web client to connect to web server and verify response. Here assert equals assert that expected and actuals are equal. This is expected and this is actual. As an example 4, we can consider this Gradle example. Here you can see the artifact ID JUnit-jupiter-api. This is in the group org.junit.jupiter. As an example 5, we can consider this Maven segment. You can see the artifact ID JUnit-jupiter-api here. This is in the group org.junit.jupiter. Here the version 5.8.2 and scope is test. As an example 6, we are now considering writing tests. Here the annotation interface at test is at test in package org.junit.jupiter.api in module org.junit.jupiter.api. At test is used to signal that the annotated method is a test method. The following example provides a glimpse at the minimum requirement for writing a test in JUnit Jupiter. Now we are considering metadata annotations and composed annotations. In annotations, at fast can then be used as a drop-in replacement for at tag fast. JUnit Jupyter annotations can be used as meta annotations. That means that you can define your own composed annotation that will automatically inherit the semantics of its meta annotations. For example, instead of copying and pasting at tag fast throughout your code base, you can create a custom composed annotation named at fast as follows. So at fast can then be used as a drop-in replacement for at tag fast. The following test method demonstrate the usage of at fast annotation. You can even take that one step further by introducing a custom fast tag annotation, at fast tag annotation that can be used as a drop-in replacement for at tag fast and at test. JUnit automatically recognizes the following as at test method that is tagged with fast. Now we are considering a standard test class in test classes and methods. Annotation interface test in package org.junit-jupiter.api in module org.junit-jupiter.api. At test is used to signal that the annotated method is a test method. The test methods and lifecycle methods may be declared locally within the current test class, inherited from superclasses or inherited from interfaces. In addition, test method and lifecycle method must not be abstract and must not return a value except at test factory methods which are required to return a value. Class and method visibility. Test classes, test methods, and lifecycle methods are not required to be public, but they must not be private. It is generally recommended to omit the public modifier for test classes and test methods and lifecycle methods unless there is a technical reason for doing so. For example, when a test class is extended by a test class in another package. Another technical reason for making public class and public classes and another technical reason for making classes and methods public is to simplify testing on a module path when using Java module system. The following test class demonstrate the usage of at test methods and all supported lifecycle methods. Not executed. Now we are considering display names. Test classes and test methods can declare custom display names via at display name with spaces and special characters and even emojis that will be displayed in test reports and by test runners and IDEs. The annotation interface display name in package junit.jupiter.api in module org.junit.jupiter.api. At display name is used to declare a custom display name for the annotated test class or test method. Here we are considering assertions. All JUnit assertions are static methods in the org.junit.jupiter.api.assertions class. The class assertions in package org.junit.jupiter.api in module org.junit.jupiter.api. Assertions is a collection of fully utility methods that support asserting conditions in tests. JUnit Jupyter comes with the many assertion methods that JUnit 4 has, and adds a few that lend themselves to being used with Java 8 lambdas. All JUnit Jupyter assertions are static methods in the org.junit.jupiter.api.assertions class. Preemptive timeout with assert timeout preemptively. The various assert timeout preemptively methods in the assert class execute the provided executable or supplier in a different thread than that of the calling code. This behavior can lead to undesirable side effects if the code that is executed within the executable or supplier relies on java.lang thread local storage. One common example of this is the transactional testing support in the Spring framework. Specifically, Spring's testing support bind transaction state to the current thread via a local thread before a test method is invoked. Consequently, if an executable or supplier provided to assert timeout preemptively invokes Spring managed component that participate in transactions, any actions taken by those components will not be rolled back with the test managed transaction. On the contrary, such action will be committed to persistent store. For example, relational database, even though the test managed transaction is rolled back. Similar side effects may be encountered with other frameworks that rely on local thread storage. A group assertion, all assertions are executed and all failures will be reported together. Within a code block, if an assertion fails, subsequent code in the same block will be skipped. Execute only if the previous assertion is valid. Grouped assertion processed independently of the result of the first name assertions. executed only if the previous assertion is valid. The following assertion succeeds. Perform task that takes less than 2 minutes. The following assertion succeeds and returns the supplied object. The following assertion invokes a method reference and returns an object. The following assertion fails and with an error message similar to exceeded timeout of 10 millisecond by 91 milliseconds. Simulate the task that takes more than 10 milliseconds. The following assertion will fails with an error message similar to execution timeout after 10 milliseconds. Simulate the task that takes more than 10 milliseconds. Here you can see the Kotlin assertion support. All JUnit-Jupyter Kotlin assertions are top-level functions in the org.junit-jupiter.api package. JUnit-Jupyter also comes with a few assertion methods that lend themselves well to being used in Kotlin. All JUnit-Jupyter Kotlin assertions are top-level functions in the org.junit-jupiter.api package. This mapping returns a stream in JUnit. The following assertion fails with an error message similar to execution timeout after 10 milliseconds. Simulate the task that takes more than 10 milliseconds. Now we are considering assumptions. All junit-jupiter assumptions are static methods in the org.junit-jupiter-api.assumptions class. The class assumptions in package org.junit-jupiter-api in module org.junit-jupiter-api. Assumptions is a collection of utility methods that supports conditional test execution based on assumptions. JUnit-Jupiter comes with a subset of assumption methods that JUnit 4 provides and adds a few that lend themselves well to being used with Java 8 Lambda expressions and method references. All JUnit-Jupiter assumptions are static methods in the org.junit-jupiter-api.assumptions class. As of Jupyter 5.4, it is also possible to use methods from JUnit-4's org.junit-assume class for assumptions. Specifically, JUnit-Jupiter supports JUnit-4's assumption violated exception to signal that a test should be aborted instead of making as a failure. Reminder of test. Reminder of test. Perform these assertions only on CI server. Perform these assertions in all environments. Now we are considering disabling test. The entire class or individual test methods may be disabled via the @disabled annotation, via one of the annotation annotation interface disabled in package org.junit-jupiter-api in module org.junit-jupiter-api. @disabled is used to signal that the annotated class or test method is currently disabled and should not be executed. Here is a @disabled test class. Here is a test class that contains a @disabled test method. @disabled may be declared without providing a reason. However, the JUnit team recommends that developers provide a short explanation for why a test class or a test method has been disabled. Consequently, these examples both show the use of a reason for example, here. Some development teams even require the presence of issue tracking numbers in the reason for automated traceability, etc. Now we are considering conditional test. Considering operating system and architecture conditions in conditional test execution. The conditional execution based on operating system. The annotation interface enabled on OS in package org.junit-jupiter-api.condition in module org.junit-jupiter-api. At enable on OS is used to signal that the annotated test class or test method is only enabled on one or more specified operating systems, so one or more specified architectures. The annotation interface disabled on OS in package org.junit-jupiter-api.condition in module org.junit-jupiter-api. At disable on OS is used to signal that the annotated test class or test method is disabled on one or more specified operating systems or more specified architectures. A container or test may be enabled or disabled on particular operating system, architecture, or combination of both via enabled at enabled OS and at disabled OS annotations. Here the conditional execution based on operating systems. Here the conditional execution based on architecture. Now we are considering tagging and filtering. Those tags can later be used to filter test discovery and execution. The annotation interface tag in package org.junit-jupiter-api in module org.junit-jupiter-api. Add tag is a repeatable annotation that is used to declare a tag for annotated test class or test method. Test classes and methods can be tagged via tag annotation. Those tags can later be used to filter test discovery and execution. Now we are considering method order in test execution order. The following example demonstrates how to guarantee that the test methods are executed in the order specified via the at order annotation. Annotation interface order in package org.junit-jupiter-api in module org.junit-jupiter-api. At order is an annotation that is used to configure the order in which the annotation element, that is field, method or class, should be evaluated or executed relative to the other elements in the same category. Although true unit tests typically should not rely on the order in which they are executed, there are times when it is necessary to enforce a specific test method execution order. For example, when writing integration test or functional test, where the sequence of test is important, especially in conjunction with at test instance the lifecycle per chart per class. To control the order in which test methods are executed, annotate your test class or test interface with at test method order and specify the desired method order, or use one of the following built-in method order implementation. Method order dot display name, short test methods alphanumerically based on their display names. Method order dot method name, short test methods alphanumerically based on their names and formal parameter list. Method order dot order annotation, short test method numerically based on the value specified via at order annotation. Method order random, orders test method pseudo randomly and support configuration of custom seed. Method order dot alphanumeric, short test methods alphanumerically based on the names and parameter list, duplicated in favor of method order dot method name to be removed in 6.0. The following example demonstrates how to guarantee that test methods are executed in the order specified via at order annotation. Perform assertions against null values. Perform assertions against empty values. Perform assertions against valid values. Now we are considering changing the default test instance lifecycle in test instance lifecycle. For example, to set the default test instance lifecycle mode to lifecycle.per class, you can start your JVM with the following system property. If a test class or test interface is not annotated with at test instance, JUnit-Jupyter will use default lifecycle mode. The standard default mode is per method. However, it is possible to change the default for the execution of an entire test plan. To change the default test instance lifecycle mode, set jupyter.instance.lifecycle.default configuration parameter to the name of an enum constants defined in the test instance lifecycle. Ignoring case, this can be supplied as a JVM system property as a configuration parameter in the launcher discovery request that is passed to the launcher or via the JUnit platform configuration file. For example, to set the default test instance lifecycle mode lifecycle.per class, you can start your JVM with the following system property here. Note, however, that the settings, the default test instance lifecycle mode via the JUnit platform configuration file is more robust solution, since configuration file can be checked into a version control system along with the project and can therefore be used within IDEs and your build software. To set the default test instance lifecycle mode to lifecycle.per class via the JUnit platform configuration file, create a file named junit-platform.properties in the root of the class path. For example, source, then test, then resources with the following content here. Changing the default test instance lifecycle mode can lead to unpredictable results and fragile builds if not applied consistently. For example, if the build configures a per class semantics as the default, but the tests in the IDE are executed using per method semantics, that can make the difficult to debug errors and that occur on the build servers. It is therefore recommended to change the default in the JUnit platform configuration file instead of via a JVM system property. Now we are considering nested test. Here is an elaborate example both as source code and as a screenshot of the execution within an IDE. The annotation interface nested in package org.junit-jupiter.api in module org.junit-jupiter.api. At nested is used to signal that the annotated class is nested non-static test class, that is an inner class that can share the setup and state with an instance of its enclosing class. The enclosing class may be a top level test class or another at nested test class, and nesting can be arbitrarily deep. At nested test give the test writer more capabilities to express the relationship among several groups of tests. Such nested tests make use of Java nested classes and facilitate hierarchical thinking about the test structure. Here's an elaborate example both as a source code and as a screenshot of the execution of IDE. Within an IDE, here's the nested test suite for testing a stack. When executing this example in an IDE, the test execution tree in the GUI will look similar to the following image here. This is executing a nested test in an IDE. In this example, preconditions from the outer tests are used in the inner test by defining hierarchical lifecycle method for setup code. For example, create new stack. Method is before each lifecycle method that is used in the test class in which it is defined, and in all levels in the nesting tree below the class in which is defined. The fact that setup code from the outer tests is run before inner tests are executed gives you the ability to run all tests independently. You can even run inner test alone without running the outer test because the setup code from the outer test is always executed. Only non-static nested classes, that is inner classes, can serve as at nested test classes. Nesting can be arbitrarily deep, and those inner classes are subject to full life cycle support with one exception. At before all, and after all methods do not work by default. The reason is that the Java does not allow static members in inner classes prior to Java 16. However, this restriction can be circumvented by annotating a nested test class with at test instance lifecycle.per class. If you are using Java 16 or higher, at before all and after all method can be declared as static at nested test class, and this restriction is this restriction no longer applies. Now we are considering test info parameter resolver in dependency injection for constructors and methods. The following demonstrates how to have a test info injected into a test constructor and at before each method and test method. Class test info parameter resolver in package junit-jupiter-engine.exe extension. The parameter resolver that resolves the test info for the currently executing test. Test info parameter resolver if a constructor or method parameter of type test info. The test info parameter resolver will supply an instance of test info correspond to the current container or test. As a value for the parameter. The test info can then be used to retrieve information about current container or test such as display name, test class, test method, and associated tags. The display name is either technical name such as the name of the test class, so test method, or custom name configured via display name. The test info acts as a drop-in replacement for the test name rule from JUnit 4. The following demonstrate how to use how to have test info injected into test constructor before each method and at test method. Now we are considering test interfaces and default methods. Here are some examples. junit-jupiter allows at test at repeat test, at parameterized test, at text factory, at test template, and at before all, at before each, at after each, and after each to be declared on interface default methods. Before all, at before all and at after at before all and at after all can either declared as static method in a test interface or on interface default methods if the test interface or test class is annotated with at test instance lifecycle.per class. Here are some examples. At extend width and at tag can be declared on test interface so that classes that implement the interface automatically inherit its tags and extensions. In your class, you can then implement these test interfaces to have them applied. Running test interface demo results in the output similar to the following. Now we are considering repeated test, executing repeated test demo with the info log level enabled. Enabled result in the following output here. The annotation interface repeated test in package org.junit.jupiter.api in module org.junit.jupiter.api. At repeated test is used to signal that the annotated method is a test template method that should be repeated in a specified number of times with the configurable display name and optional failure. The failure threshold. A repeated test demo class at the here the demonstrates several examples of repeated test. The repeated test method is identical to the example, whereas the repeated test with repetition info. Here the demonstrate this the repeated test method is you can see here, and the whereas the repeated test with repetition info demonstrate how to have instance of repetition info injected into the test to access the total number of repetition for the current repeated test. Repeated test with failure threshold demonstrate how to start a failure threshold and simulate an unexpected failure for every second repetition. The resulting behavior can be reviewed in the console launch output at the end here, and the next two methods demonstrate how to include the custom at display name for at repeated test method in the display name of each repetition. The custom display name combines the custom display name with the custom pattern that uses test info to verify the format of the generated display name. Repeat bank sign is the display name. Which comes from the at display name declaration. One divided by 1 comes from the current repetition divided by total repetition. In contrast, the custom display name with the long pattern uses after mentioned predefined repeated test dot long display name pattern. Repeated test in German demonstrate the ability to translate the display names of repeated test into foreign languages. In this case German, resulting in names for individual repetitions such as Wiederholung, Holung 115, Wiederholung 215, 5, etc. Since each before each since the before each method is annotated with at before each, it will execute before each repetition of each repeated test. We see that it's possible to obtain information about the current execution repeated test executing repeated test demo with info log level. Enable result in the following output here. When using the console launcher with the Unicode theme enabled, execution of repeated test demo result in the following output console here. Likewise, this goes to 10 repetitions. Simulate unexpected failure every second repetition. Likewise, this goes to up to repetition 10 of 10. Let's move to this one here. Then it comes to here, boom. Then here again, boom, and then threshold exceeded here. And the German repeated test in German is repeated 5 times. Likewise. Now we are considering parameterized tests. The following example demonstrates a parameterized test that uses at value source annotation to specify string array as a source of arguments. The annotation interface parameterized test in package org.junit-jupiter-params in module org.junit-jupiter-params. At parameterized test is used to signal that the annotated method is a parameterized test method. The parameterized test make it possible to run a test multiple times with the different arguments. If they are declared just like regular at test method, but use at parameterized test annotation instead. In addition, you must declare at least one source that will provide the argument for each invocation, then consume argument in test method. The following example demonstrate a parameterized test that uses value source at value source annotation to specify string array of source arguments. When executing this parameterized test method, each invocation will be reported separately. For instance, console launcher will print out similar to the following. Test templates. Now we are considering test templates. A test template method is not a regular test case, but rather a template for test cases. The annotation interface a test template in package org.junit-jupiter-api in module org.junit-jupiter-api. At test template is used to signal that the annotated method is a test template method. At test template method is not a regular test case, but rather a template for test cases. As such, it is designed to be invoked multiple times depending on a number of invocation contexts returned by the registered providers. Thus, it must be used in conjunction with a registered test template invocation context provider extension. Each method invocation of a template method behave like the execution of the regular test method with full support for the same lifecycle callbacks and extensions. Repeated test and parameter test are built-in specializations of test templates. Now we are considering dynamic tests. For demonstration purposes, the dynamic not single test method generates a single dynamic test instead of a stream, and dynamic not single container method generate a nested hierarchy of dynamic tests utilizing dynamic container. The class dynamic test in package org.junit-jupiter-api in module org.junit-jupiter-api. A dynamic test is a test case generated at runtime. The following dynamic test demo class demonstrate the several examples of test factories and dynamic tests. The first test method returns invalid return type. Since an invalid type cannot be detected at compile time, JUnit exception is thrown when it is detected at runtime. The next 6 methods demonstrate the generation of collection and iterable and iterator and array and stream of dynamic test instances. Most of these examples do not really exhibit dynamic behavior, but merely demonstrate a supported return type in principle. However, the dynamic test from stream and dynamic test from int stream demonstrate how to generate dynamic test for a given set of strings or range of input numbers. Next method is truly dynamic in nature. Generate random number of tests. Is of course next method is the The next method is truly dynamic in nature, that generates random number of tests, implements an iterator that generates random numbers. A display name generator and and a test executor, and then provides all three dynamic test.stream. Although non-deterministic behavior of generate random number tests is of course in conflict with the test repeatability and should thus be used with care, it serves to demonstrate the expressiveness and power of dynamic tests. The next method is similar to generate random number of tests in more flexibility. However, dynamic test from stream factory method generates a stream of dynamic test from existing stream via dynamic test.stream. Dynamic test.stream method, stream factory method. For demonstration purposes, dynamic not single test method generates a single dynamic test instead of a stream, and the dynamic not single container method generates a nested hierarchy of dynamic tests utilizing dynamic container. This will result a JUnit exception. Generate test for the first 10 even integers. Generates random positive integers between 1 and 100 until a number currently divisible by 7 encountered. Generate display names like input 5 input, 37 input, 85, etc. Execute test based on the current input value. Returns a stream of dynamic tests. Stream of palindromes to check. Generate display names like race car in the palindrome. Execute test based on the current input value. Return the stream of dynamic tests. Stream of palindromes to check. Returns the stream of dynamic tests. Now we are considering timeouts. The following example shows how a timeout is applied to lifecycle and test methods. A timeout annotation allows one to declare that a test of a test factory, test template, or lifecycle method should fail if its execution time exceeds the given duration. The time unit for the duration default to seconds, but it's configurable. The following example shows how a timeout is applied to lifecycle and test methods. To apply the same timeout to all test methods within a test class, all of its nested classes and all of its nested classes, you can declare a timeout annotation at the class level. It will then be applied to all test factory, test template methods within that class, and it's at nested class unless overridden by a timeout. Annotations declared at the class level timeout annotation on the specific method or nested class. Please note that the timeout annotation declared at the class level are not applied to the lifecycle methods. Declaring a timeout at test factory method checks that factory method returns within a specified duration but does not verify the execution time of each individual dynamic test generated by the factory. Please use assert timeout method or assert timeout preemptively method for that purpose. If the timeout is present on at test template method, for example at repeated test or at parameters test, each invocation will have the given timeout applied to it. Fail if the execution time exceeds 5 seconds. Fail if the execution time exceeds 500 milliseconds. Fail if the execution time exceeds 500 millisecond. The test code is executed in a separate thread. Now we are considering parallel execution. Synchronization in parallel execution. Two tests that require read access. The two tests that require read access to a shared resource may run in parallel with each other, but not while any other test that required read-write access to the same shared resource is running. Annotation interface execution in package org.junit-jupiter-api.parallel in module org.junit-jupiter-api. At execution is used to configure the parallel execution mode of a test class or test method. Enum public static final execution mode concurrent. Enum class execution mode in package org.junit-jupiter-api.parallel in module org.junit-jupiter-api. Allow concurrent execution with any other node. In addition to controlling the execution mode using at execution annotation, JUnit-Jupiter provides another annotation-based declarative synchronization mechanism. At resource lock, annotation allows you to declare that a test class or test class or method uses a specific shared resource that requires synchronized access to ensure reliable test execution. The shared resource is identified by a unique name, which is string. The name can be user-defined or one of the predefined constant in resources, system properties, system out, system error, local, or time zone. If the test in the following in example were run in parallel without the use of at resource lock, they would be flaky. Sometimes they would pass, and at other times they would fail due to inherent race condition of writing and then reading the same JVM system property. When access to shared resources is declared using at resource lock annotation, the JUnit-Jupiter-engine uses this information to ensure that no conflicting tests are run in parallel. Running tests in isolation, most of your test classes can be run in parallel without any synchronization, but you have some test classes that need to run in isolation. You can mark the latter with the at isolated annotation. Tests in such classes are executed sequentially without any other results, other tests running at the same time. In addition to the string that uniquely identifies the shared resource, you may specify an access mode. Two tests that require read access to a shared resource may run in parallel with each other, but not while any other test that requires read-write access to the same shared resource is running. Now we are considering the temp directory extension in built-in extensions. A test method that requires a temporary directory. The annotation interface temp dir in package org.junit-jupiter-api.io in module org.junit-jupiter-api. At temp dir can be used to annotate a field in a test class, so a parameter in a lifecycle method or test method of type path or file that should be resolved into temporary directory. The built-in temp directory extension is used to create a cleanup temporary directory for individual test or all tests that in test class. It is registered by default. To use it, annotate a non-final unassigned field of type java.nio.file.path or java.io.file with at temp dir or add a parameter of type java.nio.file.path or java.io.file annotated with @temp_dir to a lifecycle method or test method. For example, the following test declared a parameter annotated with @temp_dir for a single test method creates and write to a file in the temporary directory. And checks its contents. Now we are considering extension API, the overview. In contrast to the competing runner, test rule and method rule extension point in JUnit 4.0, for JUnit 4, the junit-Jupyter extension model consists of a single coherent concept, the extension API. Note, however, that the extension itself is just a marker interface. Now we are considering declarative extension registration in registering extensions. We assume the web service extension starts a local web server and injects the server URL into parameter annotated with @web server URL. The annotation interface extend with in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. @extension with is a repeatable annotation that is used to register extension for annotated test class, test interface, test method, parameter, or field. Developers can register one or more extension declaratively by annotating a test interface, test class, test method, or custom composed annotation with @extend with, and supplying the class references for extension to register. As of JUnit Jupyter 5.8, the extend with @extend with may also be declared on fields or on parameters in test class constructed, in test methods, and in before, after all, before each, and after each lifecycle methods. For example, to register web server extension for a particular test method, you would annotate the test method as follows. We assume the web server extension starts a local web server and injects the server's URL into parameters annotated with @web server URL. To register the web server, web server extension for all tests in particular class and its subclasses, you would annotate the test class as follows. Multiple extensions can be registered together like this. As an alternative, multiple extensions can be registered separately like this. Extensions registered declarative via @extend with at class level, method level, or parameter level will be executed in the order in which they are declared in the source code. For example, the execution test in both my first tests and my second test will be extended by the database extension and web server extension in exactly that order. use the web client to connect to the web server using server URL and verify the response. Now we are considering deactivating conditions in conditional test execution. For example, to deactivate JUnits at disabled condition, you can start your JVM with the following system property. Sometimes it can be useful to run the test suite without certain conditions being active. For example, you may wish to run test even if they are annotated with at disabled in order to see if they are still broken. To do this, provide a pattern for junit-jupiter-condition.deactivate configuration parameter to specify which conditions should be deactivated that is not evaluated for the current test run. The pattern can be supplied as a JVM property as a configuration parameter launcher discovery request that is passed to the launcher or via the JUnit platform configuration file. For example, to deactivate the JUnit at disabled condition, you can start your JVM with the following system property. Now we are considering a test instance pre-construct callback. Test instance pre-construct callback define the API for extension that wish to be invoked prior to the test instances being constructed by a constructor call or via test instance factory. Interface test instance pre-construct callback in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. Test instance pre-construct callback define the API for extension that wish to be invoked prior to the creation of test instances. This extension provides a symmetric call to test instance pre-destroy callback and is useful in combination with other extensions to prepare constructor parameters, so keeping track of test instances and their life cycle. Now we are considering test instance factories. Test instance factory defines then the API for extension that wish to create test class instances. Interface test instance factory in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. Test instance factory define API for extension that wish to create test instances. Common use cases include acquiring a test instance from a dependency injection framework or invoking study factory method to create a test class instance. If no test instance factory registered, the framework will invoke the sole constructor for the test class to instantiate it, potentially resolving constructor argument via registered parameter resolver extensions. Extensions that implement test instance factory can be registered on the test interface's top level test class or nested test classes. Registering multiple extensions that implement a test instance factory or for any single class will result exception being thrown for all tests that in that class in any subclasses and in nested classes. Note that test instance factory registered in a superclass or enclosing class, that is the case of at nested class, is inherited. It is a user's responsibility to ensure that only a single test instance factory registered for any specific test class. Test instance post-processing. Test instance post-processor defines the API for extensions that wish to post-process test instances. Interface test instance post-processor in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. Test instance post-processor defines the API for extensions that wish to post-process test instances. Common use case include injecting dependencies into the test instance, invoking custom initialization methods on the test instance, etc. For a concrete example, consult your source code for mock2 extension and the extension examples in documentation. Test instance pre-destroy callback. Test instance predestroy callback define the API for extensions that wish to process test instances after they have been used in test and before they are destroyed. Interface test instance predestroy callback in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. Test instance predestroy callback defines the API for extension that wish to process test instances after they have been used in test but before they are destroyed. Common use cases include cleaning the dependencies that have been injected into the test instance, invoking custom initialization methods on the test instance, etc. Parameter resolution. Parameter resolver defines the extension API for dynamically resolving parameters at runtime. Interface parameter resolver in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. Parameter resolver that defines the API for extensions that wish to dynamically resolve argument for parameters at runtime. If a test class constructs a test method or lifecycle method declares a parameter, the parameter must be resolved at runtime by a parameter resolver. Parameter resolver can either be built in or registered by the user. Generically speaking, parameters may be resolved by name, type, annotation, or any combination thereof. If you wish to implement a custom parameter resolver that resolves the parameter based solely on the type of the parameter, you may find convenient to extend the type-based parameter resolver, which serves as a generic adapter for this for such use cases. Due to the bug in bytecode generated by Java-C on JDK versions 5 to JDK 9, looking up the annotation in parameter directly via the core java.lang.reflector parameter API always fail for inner class constructor, that is a constructor in a nested test class. The parameter context API supplied to the parameter resolver implementation therefore include the following convenient method for correctly looking up the annotations on parameters. Extensions authors are strongly encouraged to use these methods instead of those provided in java.lang.reflector parameter in order to avoid this bug in the JDK. Boolean is annotated, classed question mark extended annotation type, optional A find annotation, class A annotation type, list A find repeatable annotations, class A annotation type. The other extensions can also leverage registered parameter resolvers for method and constructor invocations using executable invoker available via the get executable invoker method in the extensions context. Test result processing. Watcher defines the API for extensions that wish to process the result of the test method execution. Specifically, a test watcher will be invoked in contextual information for the following for the events. Interface test watcher in package junit-jupiter-api.extension in module junit-jupiter-api. Test watcher defines the API for extensions that wish to process test results. Test disabled invoked after disabled test method has been skipped. Test successful invoked after test method has completed successfully. Test aborted invoked after test method has been aborted. Test failed invoked after a test method failed. When it constructs to the definition of a test method presented in definitions, in this context, test method refer to any at test method or at test template method. For example, at repeated test or at parameterized test. Extensions implementing this interface can be registered at the class level, instance level, or method level. When registered at the class level, a test watcher must invoked for any contained test method, including those in the nested classes. When registered at the method level, a test watcher will only be invoked for the test method for which it was registered. If a test watcher is registered via an unstatic instance field, for example, a registration extension, and the test class is configured with at instance lifecycle.per method semantics, which is default lifecycle mode, the test watcher will not be invoked with events for at template test methods, for example, at repeated test or at parameterized test. To ensure the test watcher is invoked to all test method in a given class, it is therefore recommended that the test watcher is to be registered at the class level with at extension width or via static field with at registration as register extensions or extends with. If there is a failure at the class level, for example, exception thrown by at before all method, no test result will be reported. Similarly, if the test class is disabled via a execution condition. For example, at disabled, no test result will be reported. In contrast to the other extension in APIs, the test watcher is not permitted to adversely influence the execution of tests. Consequently, any exception thrown at the method in the test watcher API will be logged at warning level and will not be allowed to propagate or fail test execution. In instances of extension context.store.closable resource stored in the store of the provided extension context will be closed before methods in the test watcher API are invoked. You can use the parent context store to work with such resources. Now we are considering before and after test execution callbacks in test lifecycle callbacks, an extension that times and logs the execution test methods. The interface before test execution callback in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. The before test execution callback defined API for extensions that wish to provide additional behavior to test immediately before an individual test is executed, but after any user-defined setup methods. That is, for example, at before each methods have been executed for that test. Interface after test execution callback in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. After test execution callback define API for extension that wish to provide additional behavior to test immediately after the individual test has been executed, but after any user-defined setup methods, for example, after each before any user-defined setup methods, for example, at after each methods have been executed for that test. Before test execution callback and after test execution callbacks define the API for extension that wish to add the behavior that will be executed immediately before and immediately after. A test method is executed respectively. As such, these callbacks are well suited for timing and tracing and similar use cases. If you need to implement a callback that are invoked around at before and after after each methods, implement before each callback and after each callback instead. Following example shows how to use these callbacks to calculate and log the execution time of a test method. The timing extension implements both before test execution callback and after test execution callback in order to time and log the test execution. Since timing extension tests class registered the timing extension via at extend with its test will have the timing applied when they execute. The following is an example of logging produced when timing extension class extension test is run. This is the get store method. I just missed it. Now we are considering exception handling, and exception handling extension that filters the IO exception in test execution. The interface test execution exception handler in package junit-jupiter-api.extension in module junit-jupiter-api. The test execution exception handler defines the API for extension that wish to handle exceptions thrown during test execution. Exceptions thrown during the test execution may be intercepted and handled accordingly before propagating further, and so certain actions like error logging or resource releasing may be defined in specialized extensions. junit-jupiter offers API for extensions that wish to handle exceptions thrown during a test method via test execution exception handler, or for those thrown during one of the test lifecycle method, at before all, at each, at before each, at after each, and at after all via lifecycle method execution exception handler. The following examples show the extension that wish swallow all instances of IO exception, but rethrow any other exception type. Now we are considering an intercepting invocations, an extension that execute test in a user-defined thread. The interface invocation interceptor in package junit-jupiter-api.extension in module junit-jupiter-api. Invocation interceptor defines the API for extension that wish to intercept calls to test code, to the test code. Invocation interceptor defines the API for extension that wish to intercept calls to the test code. The following example shows the extension that execute all test methods at swings event dispatch thread. At test and template, now we are considering provide invocation context for test templates. A test template will accompanying extension. The interface test template test template invocation provider in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. A test template invocation context provider defines the API for extension that wish to provide one or more multiple contexts for the invocation of a test template method. A test template method can only be executed when at least one test template invocation context provider is registered. Each such provider is responsible for providing a stream of test template invocation context. context instances. Each context may specify custom display name and list of additional extensions that will only be used for the next invocation of a test template method. The following example shows how to write a test template as well as how to register and implement test template invocation context provider. In this example, the test template will be invoked twice. The display names of the invocation will be apple and banana as is specified by the invocation context. Each invocation registers a custom parameter resolver which uses the to resolve the method parameter output when using the console launcher as follows. The test template invocation context provider extension API is primarily intended for implementing different kind of tests that rely on repetitive invocation of test like method, albeit in different context. For example, with different parameters by preparing the context class instances differently or multiple times without modifying the context. Please refer the implementation of repeated test and parameter test, which use the extension point to provide their functionality. Now we are considering keeping state in extensions. Consult the corresponding Java doc for details on the methods available for storing and retrieving values via the store. Interface extension context.store in package org.junit-jupiter.api.extension in module org.junit-jupiter.api. The store provides the method for extensions to save and retrieve data. Usually an extension is initiated by only once. So the question becomes relevant, how do you keep the state of the one instances of an extension to the next? The extension context API provides store exactly for the purpose. Extension may put values into a store later for a later retrieval. It is important to remember that values stored in the extension context during the test execution will not be available in the surrounding extension context. Since the extension context may be nested, the scope of inner context may also be limited. Consult the corresponding Java doc for details on the methods available for storing and retrieving via store. Extension context.store.closable resource. An extension context store is bound to its extension context lifecycle. When an extension context lifecycle ends, it closes its associated store. All stored values that are instances of closable resource are notified by an invocation of their close method in the inverse order they were added in. Now we are considering annotation support in supported utilities in extensions. Consult the Java doc for annotation support for further details. Class annotation support in package org.junit-platform-commands.support, in module org.junit in the module org.junit-platform-commands. This is basically with the platform. The annotation support provides static utility methods for common tasks regarding annotations. For example, checking if a class method or field is annotated with a particular annotation, finding annotation on a given class method or field, finding fields or methods annotated with a particular annotation. So this is more related to Junit platform. Annotation support provides static utility methods that operate on annotation elements, packages, annotations, classes, interfaces, constructors, methods, and fields. These include methods to check whether an element is annotated or meta annotated with a particular annotation, to search for specific annotations, and to find annotated method and the fields in the class or interface. Some of these methods search on implemented interface and within class hierarchies to find annotations. Now we are considering relative execution order of use code and extensions. Here, wrapping behavior of callbacks. All methods imported statistically from a logger class log contextual information in order to help us better understanding of the execution order of the user applied callback and callback methods in extensions. Before each callback in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. The before each callback defines the API for extension that wish to provide additional behavior to test before an individual test and any user-defined set of methods. For example, at before each methods for that test have been executed. Interface after each callback in package org.junit-jupiter-api.extension in module org.junit-jupiter-api. After each callback define the API for extension that wish to provide additional behavior to test after the individual test and any user defined tear down methods. For example, after each methods for that have been executed. Junit-Jupyter always guarantees the wrapping behavior of the multiple register extensions that implement the lifecycle callback, such as before all callback, after all callback. Before each callback, after each callback, before test execution callback, and after test execution callback. That means that the given two extension 1 and extension 2 with extension 1 registered before extension 2, any before callback implemented by extension 1 are guaranteed to execute before callbacks implemented by extension 2. Similar, given the two extension registered in the same order and any after callbacks implemented by extension 1 is guaranteed to execute after any after callbacks implemented by execution 2. Extension 1 and extension 2 therefore set to wrap extension 1 is therefore set to wrap extension 2. Junit-Jupyter also guarantees the wrapping behavior within class and interface hierarchies for users applied lifecycle method. Before all, methods are inherited from the superclass as long as they are not hidden, overridden, or superseded, that is replaced based on the signature only, irrespective of Java visibility rules. Therefore, before all methods from the superclass will be executed before all methods in the subclass. Similarly, that before all methods declared in an interface are inherited as long as they are not hidden, overridden, and before all methods from the interface will be executed before all methods in the class that implement the interface. After all, methods are inherited from the superclass as long as they are not hidden, overridden, or superseded. That is replaced based on the signature only, irrespective of Java visibility rules. Therefore, after all methods from the superclass will be executed after all methods in the subclass. Similarly, after all method declared in the interfaces are inherited as long as they are not hidden or overridden, and after all methods from the interface will be executed after all methods in that class implements the interface. Before each methods are inherited from the superclass as long as they are not overridden or superseded. That is replaced based on the signatures only and irrespective of Java visibility rules. Therefore, before each methods from the superclass will be executed before each methods in the subclass. Similarly, before each methods declared as interface default methods are inherited as long as they are not overridden, and before each default method will be executed before each methods in this class implements the interface. After each methods are inherited from the superclass as long as they are not overridden or superseded, replaced based on the signature and irrespective of Java visibility rules. Therefore, furthermore, after each method from the superclass will be executed after each method in the subclass. Similarly, after each method declared as an interface default methods are inherited as long as they are not overridden, and after each default method will be executed after each methods in the class that implements the interface. Following examples demonstrate that behavior. Please note that the example do not actually do anything realistic, instead of mimic the common scenarios for testing interaction with the database. All methods important statistically for the logger class log contextual information in order to help us better understanding of the execution order of the supplied callback method and callback methods extensions. Now we are considering junit-jupiter in dependency metadata. The junit-jupiter API in artifact ID junit-jupiter API in group ID octo junit-jupiter. junit-jupiter API for writing tests and extensions. As an exception example, we can consider the squad segment. Here the method public static t extend throwable t assert throws class t expected value and executable here. Assert that execution of the supplied executable throws an exception of the expected type and returns the exception. If no exception is thrown, or if the exception is of a different type is thrown, this method will fail. If you do not want to perform additional checks on the exception instance, ignore the return value. This method is in class assertions. As an error example, we can consider this error occurred in the environment JUnit and Maven project. This error occurred in JUnit and Maven project in NetBeans. Error package org.junit-jupiter-api does not exist. Now we are focusing on junit-jupiter-engine. JUnit-Jupiter test engine implementation only required at runtime. As an example, we can consider package org.junit-jupiter-engine, core package for the JUnit-Jupiter test engine. This is in module org.junit-jupiter-engine. As an example 2, we can consider default Jupyter configuration class, default implementation of the Jupyter configuration API. This is in the module org.junit-jupiter-engine and package org.junit-jupiter-engine.config. As an example 3, we can consider this code segment. Here you can see the class Jupyter test engine, the JUnit Jupyter test engine. Here you can see the method public test description discover here, engine discovery request and unique ID here. This method discovers test according to the supplied engine discovery request. This class is in module org.junit-jupiter-engine and package the org.junit-jupiter-engine. Here the supplied unique ID must be used as the unique ID of the returned root test descriptor. Here the engine discovery request provide the test engine access to the information necessary to discover test and containers. And the unique ID encapsulates the creation and passing and display unique IDs for test descriptors. The interface test descriptor, the mutable descriptor for a test or container that has been discovered by a test engine. Here you can see the Gradle segment for additional Gradle dependencies for IntelliJ IDEA. Here you can see artifact ID junit-jupiter-engine, module junit-jupiter-engine of JUnit 5, junit-jupiter-test-engine implementation only required at runtime here. This is in the group ID org.junit.jupiter. You can see this one, junit-jupiter-engine. As an example 5, we can consider this Maven segment for additional Gradle dependencies for IntelliJ IDEA. Here you can see artifact ID junit-jupiter-engine, module junit-jupiter-engine of JUnit 5, junit-jupiter-test-engine implementation only required at runtime. This is in the group ID org.junit.jupiter. Now we are considering registering a test engine in test engines. For example, the junit-jupiter-engine module registers org.junit-jupiter-engine.test Jupyter test engine in a file named org.junit-platform-engine.test-engine within the /meta-info/services folder in junit-jupiter-engine jar. A test engine registration is supported via Java's service loader mechanism. Now we are considering junit-jupiter in dependency metadata. Artifact ID junit-jupiter-engine in org.junit.jupiter. junit-jupiter test engine implementation only required at runtime. As an exception example, we can consider test execution exception handler, interface test execution exception handler. This is a functional interface and can therefore be used as the assignment target for a lambda expression or method reference. This is in the package org.junit.jupiter.api.extension. Now we are focusing on other tests. As an example, we can consider this code segment. Here 3 test cases for a new engine. This following example annotates the test class with the ampersand web smoke test. To identify the test classes, it contains 3 separate test cases. Identified by simple field, and each field is annotated with ampersand get, denoting the need to execute an HTTP get request. Supporting post or other HTTP verbs would be just as simple. The target URL of the request is specified in the value of the field. As mentioned usually you have complete freedom in the new test engine regarding how to design a test model. You might have used method as most traditional test engine do, or you might have specified the expected value as a method return type. All are perfectly valid options. Here you can see the execution of the main engine class in the IDE. Here you can, as an error example, you can see here you can see the execution of the main engine class in the IDE. As can be seen in this figure, the project, the specific project here uses domain-specific custom display names to reference to the individual test cases in the GUI of the execution IDE. Thus, in this case, you can even display the whole test definition, the URL, and the expected status code right next to the IDE symbol indicating success or failure. Such flexibility is enabled by the descriptor module, referring the freeing the IDE from the need to mechanically display plain method or field names in all cases. Here you can see the failure here. Now we are focusing on third party. As an exception example, we can consider this. If any third party test engine claims to be JUnit-Jupiter or JUnit-vintage, an exception will be thrown, immediately halting execution of the JUnit platform. As an error example, we can consider this occurred in the environment with Java 8. Here, warning third-party test engine implementations are forbidden to use the reserved JUnit prefix for their ID JUnit platform suite. Then org.junit-platform-launcher.core.default launcher, handle throwable, etc. Now we are focusing on custom API. Here you can see the execution of a single test. The execute test method is responsible for sandwiching the actual execution call between lifecycle events. The execute text field method retrieve the URL and the expected status code, and then actually execute HTTP request via a purely technical helper method. If a response is received, the method checks the actual status code and creates a test execution result.failed result failed with an assertion failed error in case the response does not meet the expectation. If sending the request throws an exception, it is wrapped in a more technical runtime exception and text execution result and test execution result dot failed result. If all goes well, the method returns a text execution result successful result. This basically is the complete custom test engine. Now we are focusing on custom engine. Here you can see JUnit 5 platform architecture. Contrary to the public opinion, JUnit 5 is a platform rather than simple test runner. To understand the need for such platform, it is helpful to take a look at some JUnit history. Early versions of JUnit were not designed with tool integration in mind. Due to wild success of these early versions, however, IDEs and build tools began integrating JUnit into their environments quite soon. However, because JUnit was not designed to be executed from third-party process, integrators sometimes had to rely on dangerous mechanisms such as reflection to make things work. In such integrations were naturally brittle and were very hard to change and maintain because the outside world relied upon and was coupled to JUnit's internals, even private members. In an infamous example for this coupling is the breaking of the integration in widely used IDE when a JUnit 4.x version changed the name of the private field. The situation was only exacerbated by other test libraries and frameworks mimicking JUnit structure to leverage JUnit's IDE integration. Therefore, while planning and designing the new generation of JUnit, and the JUnit team took special care to avoid coupling. As a matter of fact, the team invited representative from their major IDEs and build tools to kick off meeting in October 2015 to discuss a solid foundation for integration architecture. The main goal was to provide a different API for different groups of users, namely an engine service provider interface (SPI), JUnit platform-engine for integrators of existing test engines and authors of new test engines, or a launcher API, JUnit platform-launcher for IDEs and build tools to provide stable and transparent means of integrating all test engines. An annotated based API JUnit-Jupyter API for test authors, which would be similar in look and feel to JUnit for X generation, but with the more flexible extension model. The first two are the core component of JUnit 5 platform, and this figure shows the essential parts of the JUnit 5 platform and several engines built upon it. This clear separation of concerns is fundamental to the new architecture and has so far served well to avoid problematic coupling. As a consequence, the JUnit platform has been integrated into all major IDEs and build tools using Launcher API. Similarly, the platform-engine SPI has been used to integrate various test engines with the JUnit 5 platform. This allows the test engine authors to concentrate on the test definition and execution concerns and completely disregard the aspects of launching their test cases from IDEs and build tools. A special case is, of course, JUnit's own Jupyter test engine, which uses a new JUnit 5 test model. However, even this built-in engine uses only the public API and has no secret access to other parts of JUnit 5. To show how easy it is for engine authors to integrate tools with the JUnit platform, for example, you will develop a very small test engine from scratch, and we name it as WebSmoke here. Here, test engines WebSmoke, JQ, Wick, and junit-jupiter are in test engines, and WebSmoke and JQ and JUnit-Jupyter are connected to JUnit-platform-engine SPI. SPI, JUnit-platform-engine, and API, JUnit-platform-launcher are in JUnit platform. API, JUnit-platform-launcher is connected to JUnit-platform-engine. Tool IDE, build tools are in third-party tooling, and tool IDE and tool build tools are connected to API, JUnit-platform-launcher. Here you can see an implementation of a custom test engine. Interface test engine. Test engine facilitates discovery and execution of tests for a particular programming model. For example, JUnit provides a text engine that discovers and executes tests written using JUnit-Jupyter programming model. Every test engine must provide its own unique ID. Discover tests from engine discovery requests. And execute those tests according to execution requests. in order to facilitate test discovery within IDEs and tools prior to launching the JUnit platform, test engine implementations are encouraged to make use of ampersand testable annotation. For example, the ampersand text and ampersand test factory annotations in junit-jupiter are meta-annotated with ampersand testable. From most JVM languages, being the test model on classes and methods seems a natural fit. However, other test definition models, in principle, as long as individual tests can be described unambiguously by an org.junit-platform-engine.test description implementation. Typically, a test description implementation has to be provided by a test engine author and represent a testable element of the given programming model, such as a single test, field test descriptor, or container of test class test descriptor. For the purpose of this example, we want to implement an engine that is both small and lightweight. Hence, we could contemplate alternatives to a method-based test model. One option might be to use lambdas assigned to fields, because lambdas can be considered a form of lightweight methods. This is possible since we could use java.util.function.predicate implementation using aptly named method boolean test tt for test execution and boolean as a success or failure indicator. While such lambdas might be a bit more lightweight than full-blown method, maybe we can take a bit further. As mentioned before, there can be different reasons for creating custom engine. Here you want to support the requirement of a special domain in such way that creating tests becomes very simple for test author. As a simple yet still useful example, we pick the domain HTTP based mock tests. In this case, the test that merely test whether a URL works. Specifically, you need a succinct way to define the URL against which the mock test would be executed. A simple means to specify expected HTTP status code. Consider the test successful if the GET request against the specified URL result in the specified HTTP status code. As for the behavior, the degrees of freedom are extremely limited. A mock test always does the same thing, namely and execute HTTP requests against a certain Since this test does not need variants in behavior, you can get rid of methods will explicitly program statement entirely, or lambdas for that matter. You can choose completely declarative approach. When you design a custom test engine, it is important to understand the contract between a test engine and a JUnit platform. This contract is defined by org.junit-platform-engine.testengine. Interface would look here: string get ID, test descriptor discover, engine discovery request, unique ID, and execute, void execute, execution request, request. Apart from some optional metadata, this interface contains the three core responsibilities of a test engine. These core responsibilities are identification. The engine must provide a unique string by which it can be referenced and differentiated from other engines on the class path. For example, Jupyter's ID is JUnit-Jupiter. Discovery. Engine must be able to inform the JUnit platform about everything it considers its own test cases. These are arranged in a tree structure with the return test descriptor. Execution. When requested by the platform, the engine must be able to execute a given execution request. This request contains a test descriptor referencing the test to be run and provides the engine execution listener to the engine. The former previously returns the engine's own discover method. The latter is used by the engine implementation to fire test lifecycle events such as execution started, execution finished. In many cases, test engines will support a hierarchical test definition model mirroring Java's hierarchical structure of packages, classes, and methods. The JUnit platform provides special support for such hierarchical engine in the form of the org.junit.platform.engine.support.hierarchical test base class. JUnit's own Jupyter test engine is itself an extension of this base class. By using this support, advanced features such as parallel execution can be readily reused by the custom engines. However, for the sake of simplicity and clarity, WebSmoke test will not use this base class. It will implement the required interfaces directly. Implementing the minimum test engine here. A test engine usually consists of the engine class itself and one or more test description implementations. This is in no way mandatory. And in this example here there are two annotations. This is no mandatory when designing this exercise here. We happen to choose an annotation based testing model. For such implementation, JUnit platform provide a good support with the org.junit.platform.commons.support.annotation support utility. Here that you can see the integration, discovery, and execution work. The discover engine discovery request, unique ID methods creates an engine descriptor and add test descriptions hierarchically while engine discover request gives access to the several implementation of org.junit.platform.engine.discovery selector. Such selectors can be reference various structural elements in Java such as method classes, packages, and whole class path or the file system, file directories, as well as JUnit's own unique ID instances. Basically, the such selectors can reference various structural element of Java such as method, such as methods, classes, packages, and whole class path. Or the file system, files, directories, as well as JUnit's own unique ID instances. The test engine uses these to indicate to the requesting tool such as IDE what it considers test cases associated with every such element according to a specific test model. The last method here takes care of test execution. Execute execution request, accept an execution request, and delegates most of his actual work to a helper class named smoke test executor. In this class, the various test descriptor variants are handled and individual tests are executed. As an example too, we can consider this the JUnit configuration file using the Java SPI mechanism. Test engine integration. This test engine class can be immediately executed in an ID such as IntelliJ IDEA if two conditions are fulfilled. First, you need to test engine code on the class path, typically in a Maven or Gradle dependency. Second, the new engine must be registered with the JUnit platform. This is done via Java's well-known SPI. To this end, the special file must be present in the class path, as you can see in this figure. For the SPI mechanism to work, the file name must specify the SPI. Here names the org.junit-platform-engine.testengine. The file contains only one line, the fully qualified name of the main engine class, which in this case is the org.example.websmoke.engine.websmoke-testengine. This FQN must refer to a class implementing the interface specified by the file name. When the main engine class is executed in the IDE, the test result should display. As an example 3, we can consider this one using test engine test kit. Using engine test kit, a simple integration test for your custom test engine look as follows. You made a good progress with the implementation of a new custom test engine now, and you also tried out by running some example test in that IDE. Everything seemed to work, but however, as a professional developer, you would like to have a more rigorous approach to validate the new test engine. You may also want a way of running systematic and automatized test of the engine. After all, this is the key paradigm of any form of test-centered development. First approach might be to use a new test engine to test itself. While this can add some extra assurance, it does not suffice, because if you use test engine to test itself, you might fall for error masking. That's when you might not find a bug in the implementation because another buggy part of the engine hides that failure. In addition to that, the example test engine is a domain specific tool for a web-smoke testing, and it is thus not capable of asserting the general correctness of software. Enter engine test kit, or more specifically the module junit-platform-test kit is a special integration testing tool provided by JUnit Platform. Engine test kit is intended to test the interplay between JUnit Platform and the custom engine implementations. The class org.junit-platform-testkit.engine test kit provides an entry point to a Fluent API exposing test event. This offers a fine-grained assertion possibilities for comparing expected lifecycle events to actual ones. Using the example begins by proclaiming interest in your custom test engine, referenced by its engine ID, which is websmoke-test. Next, you can use one of many org.junit-platform-engine.discovery select implementations to narrow the scope down to the example class from here, example web smoke test. Next, execute the selected test much in the same way an IDE would. This give you an access and org.junit.platform.testkit.engine.events instance upon which various checks can be performed. In this example, engine test kit checks, the 3 tests were executed, 2 of which were completed successfully and 1 that reported the failure. This is what you should expect. You should have expected here. You can use so that the custom web smoke test can be run in an IDE just like standard JUnit Jupyter tests. One interesting feature of the JUnit platform is the ability to execute different test engine in a single run. In the past, IDEs could implement such combined execution on their own, but the JUnit platform allows this consistency for all environments that connected via junit-platform-launcher. To demonstrate this, add the simple JUnit Jupyter test and have it execute together with the custom test engine tests. Here the class engine test kit. Engine test kit provides the support for executing a test plan for a given test engine and then accessing the result via a Fluent API to verify the expected result. Here the engine create an execution of engine test kit.builder for the test engine with the supplied ID. The test engine will be loaded via the Java service loader mechanism analogous to the manner in which test engines are loaded in the JUnit-platform-launcher API. Here select the method selectors, add all the supplied discovery selectors. The method execute tests for the configured test engine. Discovery selectors, discovery filters, and configuration parameters, and returns recorded test engine execution results. The method events or the test events, get recorded events for the test. In this context, word test applies to test descriptors that run the true from test descriptor.isTest method. Assert statistics for the events contained in this events object. Started, specify the number of expected started events. Succeeded, specify the number of expected succeeded event. Failed, specify the number of failed events. The example here, the example test class has 3 test cases and 2 successes and 1 failure. As an example 4, to demonstrate that this in IDE tests for different test engines are shown in a single graphical test execution 3 in the IDE. To demonstrate this combined execution is also portable over execution environments. You can start the standalone JUnit console runner with options like following. Here the console launcher options -e or dash include engine provide ID of an engine to be included in the test run. This option can be repeated. As a result, you get a nicely colored console output here. Considering custom test engines in test engines, you can contribute your own custom engine by implementing the interfaces in the junit-platform-engine module and registering your engine. The interface test engine in package org.junit-platform-engine and module in module org.junit-platform-engine. A test engine facilitates discovery and execution of tests for a particular programming model. Package org.junit-platform-engine in module org.junit-platform-engine public API for test engines. This is in the platform. Every test engine must provide its own unique ID discover test from for an engine discovery request and execute those tests according to an execution request. The JUnit unique ID prefix is JUnit-unique ID prefix is required for test engine from the JUnit team. The JUnit platform launcher enforces that only test engine implementation published by the JUnit team may use the JUnit- prefix for their test engine IDs. If any third-party test engine claims to be junit-jupiter or junit-vintage, an exception will be thrown, immediately halting the execution of the JUnit platform. If any third-party test engine that uses the JUnit- prefix for its ID, a warning message will be logged. Later releases of the JUnit platform will throw an exception for such violations. In order to facilitate test discovery within IDEs and tool prior to launching the JUnit platform, test engine implementations are encouraged to make use of @testable annotation. For example, @test and @test factory annotations in JUnit-Jupiter are meta annotated with @testable. Consult your Java doc for @testable for further details. If your custom test engine needs to be configured, consider allowing users to supply configuration via configuration parameters. Please note, however, that you are strongly encouraged to use a unique prefix for all configuration parameters supported by your test engine. Doing so will ensure that there are no conflicts between the names of your configuration parameters and those from other test engines. In addition, since configuration parameters may be supplied as a JVM system properties, it is wise to avoid conflict with the names of other system properties. For example, JUnit-Jupiter uses JUnit.jupiter as a prefix for all of its supported configuration parameters. Furthermore, as with the warning above regarding the JUnit- prefix for test engine IDs, you should not use JUnit as a prefix for JUnit as a prefix for names of your own configuration parameters. Although there is currently no official guide on how to implement a custom test engine, you can consult the implementation of JUnit test engines or the implementation of third-party test engine listed in the JUnit 5 wiki. You will also find various tutorials and blogs on the internet that demonstrate how to write custom test engine. Hierarchical test engine is a convenient abstract-based implementation of test engine SPI used by the junit-jupiter-engine that only required implementers to provide the logic for test discovery. It implements execution of test descriptors that implement the node interface, including support for parallel execution. As an error example, we can consider this one, execution of the main engine class in the IDE, and you can see here the fail test is in the environment IntelliJ IDEA. Now we are focusing on platform. The JUnit platform serves as a foundation for launching testing frameworks on the JVM. It also defines the test engine API for developing testing framework that runs on the platform. Furthermore, the platform provides a console launcher to launch the platform from the command line, and the JUnit platform suite engine for running a custom test suite using one or more test engines on the platform. First class support for the JUnit platform also exists in the popular IDEs. See IntelliJ IDEA, Eclipse, NetBeans, and Visual Studio Code, and build tools check like Gradle, Maven, and Ant. Here you can see a dependency diagram. In org.junit.platform, you can see JUnit platform test kit, JUnit platform suite, JUnit platform suite engine, JUnit platform suite commands, JUnit platform suite API, JUnit platform-runner, JUnit platform-JFR, JUnit platform-launcher, JUnit platform-console, JUnit platform reporting, JUnit platform-engine, JUnit platform commands. As an Maven example, we can consider this segment. Here you can see group ID org.junit.platform, JUnit platform. As a Gradle example, we can consider this one. IntelliJ IDEA supports here IntelliJ IDEA Gradle additional Gradle dependencies. IntelliJ IDEA supports running tests on the JUnit platforms since version 2016.2. Or not, however, that it is recommended to use IDEA 2017.3 or newer, since newer versions of IDEA will download the following jars automatically based on the API version used in the project: JUnit Platform-Launcher, junit-jupiter-engine, and junit-vintage-engine. IntelliJ IDEA releases prior to IDEA 2017.3 bundle specific versions of JUnit 5. Thus, if you want to use a newer version of junit-jupiter, execution of the test within the IDE might fail due to version conflict. In such cases, please follow this. In order to use different JUnit 5 version, for example 5.9.0, you may need to include corresponding versions of JUnit Platform-Launcher, junit-jupiter-engine, and junit-vintage-engine jars in the class path. Here you can see the group ID org.junit.platform in JUnit platform. Here you can see artifact ID as an example. We can consider as artifact ID JUnit platform console is standalone, an executable jar with all dependencies included is provided in Maven Central under JUnit platform console standalone directory. This is under group ID org.junit.platform. As an example 4, we can consider artifact ID JUnit platform JFR provides a launcher discovery listener and text test execution listener for Java flight recorder events on the JUnit platform. This is in the group org.junit.platform. As an example 5, we can consider JUnit platform reporting artifact, test execution listener implementations that generate test reports, typically used by IDEs and build tools. This is in group ID org.junit.platform. As an example 6, we can consider artifact ID JUnit platform suite. JUnit platform suite artifact that transitively pulls in dependencies on JUnit platform suite API and JUnit platform-surefire-engine for simplified dependency management in build tools such as Gradle and Maven. This is in the group ID org.junit.platform. As an example 7, we can consider artifact ID JUnit platform suite API. Annotations for configuring test suites on the JUnit platform. This is in group ID org.junit.platform. As an example 8, we can consider JUnit platform suite commons artifact. JUnit platform suite commons support is common support utilities for executing test suites on the JUnit platform. This is in group ID under the group ID org.junit.platform. As an example 9, we can consider artifact ID JUnit platform-surefire-engine, engine that executes test suites on the JUnit platform, only required at runtime. This is in the group ID org.junit.platform. As an example 10, we can consider artifact ID JUnit platform test kit. Provides support for executing a test plan for a given test engine and then accessing the results via a Fluent API to verify the expected results. This is in group ID org.junit.platform. Considering JUnit platform, the legacy XML format in JUnit platform reporting. Legacy XML report generating listener generates a separate XML format for each route and the test plan. Class the legacy XML reporting generating listener in package org.junit platform.reporting.legacy.xml in module org.junit.platform.reporting. Legacy XML reporting generating report generating listener is a test execution listener that generate a separate XML report for each route in the test plan. Note that the generated XML format is compatible with the de facto standard for JUnit 4 based test reports that was made popular by Ant build system. The legacy XML report generating listener is used by console launcher as well. Now we are considering Groovy DSL in open test reporting XML format in JUnit platform. For Gradle, writing an open test reporting compatible XML report can be enabled and configured via system properties. The following samples configure its output directory to be the same directory Gradle uses for its own XML reports. The command line argument provide is used to keep the task relocated across different machines, which is important when using Gradle build cache. Here's the Groovy DSL. Here Kotlin DSL. Here the console launcher. When using console launcher, you can enable test reporting output by setting configuration parameters via --config. Now we are considering required dependencies in setup in junit-platform-surefire-engine. junit-platform-surefire API in test scope. Artifact containing notification annotations needed to configure a test suite. junit-platform-surefire-engine in test runtime scope. Implementation of the test engine API for declarative test suites. Now we are considering a suite example. At suite example, as seen in the following example, selector and filter annotations can then be used to control the content of the suite. Annotation interface at suite in package org.junit-platform-suite.api in module org.junit-platform-suite.api. At suite marks a class as a test suite on the JUnit platform. By annotating a class with at suite is marked as a test suite on the JUnit platform. As seen in the following example, select and filter annotations can be used to control the contents of the suite. Additional configuration options. There are numerous configuration options for discovering and filtering tests in test suite. Please consult the Java doc of the org.junit-platform-suite.api package for a full list of supported annotations and further details. Now we are considering engine test kit in JUnit platform test kit. The key entry point into this API is the engine test kit, which provides a static factory method named engine and execute. Class engine test kit in package org.junit-platform-testkit.engine in module org.junit-platform-testkit. The engine test kit provide support for executing a test plan for a given test engine and then accessing the result via a Fluent API to verify the expected results. The org.junit-platform-testkit.engine package provides support for executing test plan for a given test engine running on the JUnit platform and then accessing the result via a Fluent API to verify the expected result. The key entry point into this API is the test engine kit, which provides a static factory methods name, engine, and execute. It is recommended that you select one of the engine variants to benefit from the Fluent APIs for building a launch discovery request. If you prefer to use the launch discovery request builder for the launch API to build your launch discovery request, you must use one of the execute variants in the test engine. For the sake of brevity, the following how to test the in JUnit Jupyter test engine, whose unique engine ID is junit-jupiter. If you want to test your own test engine implementation, you need to use its unique engine ID. Alternatively, you may test your own test engine by supplying an instance of it to the test engine to the engine test kit test engine static factory method. Now we are considering asserting statistics in JUnit platform test kit. For details on what statistics are available, consult the Java doc for event statistics. The class event statistics in package org.junit-platform-testkit.engine in module org.junit-platform-testkit. Event statistics provides a Fluent API for asserting statistics for events. Following test class written using junit-jupyter will be used in this example here. One of the most common features of the test kit is that the ability to assert statistics against event fired during the execution of a test plan. The following tests demonstrate how to assert statistics for containers and tests in the JUnit Jupyter test engine. For details on what statistics are available, consult the Java doc for event statistics. Here the select the JUnit Jupyter test engine. Select the then select example test case test class. Here the execute the test plan, and here the filter by the container events, and here the assert statistics for contain events. Here the filter by here again select JUnit Jupyter-engine, Jupyter test engine. Here the select the example test case test class. Hit here the execute the test plan. Here the filter by test events. So here the assert statistic for test events. In the verify Jupyter container stats methods, test methods, the counts for start and count for the started and succeeded statistics are true, since the Jupyter test engine and the example test case class are both considered containers. Sorry, the contain events here, the this one succeed, and here started, and here is skipped, and here aborted, and here the following throws an arithmetic exception divided by 0. Now we are considering asserting events. For example, if you want to verify the reason that the skip test method in the example test case was skipped, you can do that as follows. Here the class events in package org.junit-platform-test-kit.engine in module org.junit-platform-test-kit. Test-kit event is a facade that provides a fluent API for working with events. If you find asserting statistic alone is insufficient for verifying the expected behavior for test execution, you can work directly with the recorded event element and perform assertions against them. For example, if you want to verify the reason that the skip test method in the example test case was skipped, you can do that as follows. Here the assert that events method in the following example is a shortcut for org.assert.j.co.api.assertions.assert that events events list method for list from assert j assertions library. For details on what conditions are available for use with assert j assertions against event, consult the Java doc for event conditions. Here the select junit-jupiter-test-engine. Here then here the select the skip test method in the example test test case test class. Here the execute the test plan. Here the filter by test events. Here the save the test event on to a local variable. And here optionally assert the expected statistics. And here the assert that the recorded test event contain exactly one skip test named skip test with for demonstration purposes as the reason. Now we are considering mandatory requirements in test engines for interoperability with build tools and IDEs. The test engine implementations must adhere to the following requirement. The test descriptor returned from test engine.discoverer method must be the root of the tree of the test descriptor instances. This implies that there must not be any cycles between a node and its descendants. A test engine must be able to discover unique ID selectors for any unique ID that's previously generated, then return from the test engine.discoverer. That enables selecting a subset of tests to execute and or return. The execution skipped, execution started, execution finished methods of the test engine execution listener passed to the test engine.execute method must be called for every test descriptor node in the tree returned from the test engine discoverer at most once. Parent nodes must be reported as started before their children and as finished after their children. If a node is reported as skipped, there must not be any events reported for its descendant. An exception example we can consider JUnit exception, class JUnit exception, base class for all runtime exceptions thrown by JUnit. This is in the package org.junit.platform.commons. Now we are focusing on junit-platform-engine, public API for test engines. As an main example, we can consider this segment. Here you can see artifact ID junit-platform-engine. As an example, we can consider package org.junit.platform.engine, public API for test engines. This is in the module org.junit.platform.engine. Engine. And also the module org.junit.platform.engine also public APIs for test engines, provides the test engine interface, test discovery, and execution reporting support. As an example 3, we can consider suit test engine, class suit test engine, the JUnit platform suit test engine. This is in the module org.junit.platform.suit.engine and in the package org.junit.platform.suit.engine. As an example, example 4, we can consider registering test engine. For example, junit-jupiter-engine module registers its org.junit.jupiter.engine.jupiter test engine in file named org.junit.platform.engine.test-engine within the /meta-inf/services folder in the junit-jupiter-engine jar. Test engine registration is supported via Java service load mechanism. The following example shows how to use org.junit.platform.engine.test engine. Interface test engine. A test engine facilitates discovery and execution of test for a particular programming model. Test engine registration is supported via Java service load mechanism. This test engine is in module org.junit.platform.engine and package org.junit.platform.engine. Class service loader, a facility to load implementations of a service. public static service loader load, and class loader. Create a new service loader for the given service type and class loader. The service loader class is in module java.base and in package java.util. Here you can see a can be loaded cost in the JVM, and this is in the test class loader, but not available to the class loader. As an example 6, we can consider this. Here the interface configuration parameters that test engines may use to influence test discovery and execution. For example, junit-jupiter-engine uses a configuration parameter to enable IDE and build tools to deactivate conditional test execution. And optional boolean get boolean string key, get the boolean configuration parameter stored under the specified key. This is in module org.junit.platform.engine and package org.junit.platform.engine. Now we are considering junit platform in dependency metadata, and it's the artifact ID junit-platform-engine in group ID org.junit.platform, the public API for test engines. Exception example occurred in as an example, we can consider this code segment, this error information, exception information in the environment JUnit 5 with Eclipse, Java lang no class def found error, etc., and caused by caused by Java lang class not found exception, org.junit.platform.engine.configuration parameters at java.base JDK internal loader built-in class loader load class built-in class loader.java, etc. As an error example, we can consider this exception in thread main java.lang.bootstrap method error, etc., and then caused by java.lang.no such method error, org.junit.platform.engine.testDescription.prune we add, etc. Now we are focusing on junit-platform-launcher, junit-platform-launcher, public API for configuring and launching test plans, typically used by IDEs and build tools. Here you can see the artifact ID platform junit-platform-launcher. This is in group ID org.junit.platform. As an additional Gradle dependencies for IntelliJ IDEA, we can consider this code segment as example 2 with Gradle. You can see the artifact ID JUnit-platform-launcher here. This is in the group ID org.junit.platform. As an example 3, we can consider org.junit.platform.launcher module, public API for configuring and launching test plans. As an example 4, we can consider this code segment regarding discovering tests. Here interface launcher. The launcher API is the main entry point for client code that wishes to discover and execute tests using one or more test engines. Here the test plan discover, launch, discovery request, discover tests and build a test plan according to the supplied launcher the discovery request by querying all the registered engines and collecting their results. This is in module org.junit.platform-launcher and package org.junit.platform-launcher. Having test discovery as a dedicated feature of the platform itself frees IDE and build tools from most of the difficulties they had to go through to identify the test classes and test methods in previous versions of JUnit. You can select classes, methods and all classes in a package, or even search for all tests in a class path or module path. Discovery takes place across all participating test engines. The resulting test plan is a hierarchical and read-only description of all engines, classes and test methods that fit the launcher discovery request. The client can reverse the tree, retrieve details about a node and get a link to that original source like class, method or file position. Every node in the test plan has a unique ID that can be used to invoke particular test or group of tests. Clients can register one or more launcher discovery listeners, implement listener implementations via the launcher discovery request builder to gain insight into events that occur during the test discovery. By default, the builder registers an abort on failure listener that aborts test discovery after first discovery failure encountered. The default launcher discovery listener can be changed via junit.platform.discovery-listener discovery.listener.default configuration parameter. Here the launcher discovery builder provides a lightweight DSL for generating a launcher discovery request. Here the request create a new launcher discovery request builder. Here the method selectors add all the supplied selectors to the request. Here select package, the static method create package selector for supplied package name. Here select class method create class selector for the supplied class. Here the filters method add all the supplied filters to the request. And here the build the launcher discovery request that has been configured via the builder, via this builder. Launcher session. Here launcher factory a factory for creating launcher instances by invoking create launcher config. Here open session method, public static launcher session open session method, factory method for opening a new launcher session using the default launcher config. interface launcher session here. The launcher session API is the main entry point for client's code that wishes to repeatedly discover and execute tests using one or more test engines. Here launcher, get launcher, get the launcher associated with this session. And here discover additional test plans or execute tests. Here you can see executing test as example 5 here. Here public here void execute launcher discovery request, then execute listeners. This method execute test execute a test plan which is built according to the supplied launcher discovery request. By queuing all the registered engines and collecting their results. And here execute test plan, then text execution listeners, execute the supplied test plan, and notify registered listeners about the progress and results the execution. To execute test, client can use the same launcher discovery request. Test progress and reporting can be achieved by registering one or more test execution listeners. Listener implementation with the launcher as in this example here. There's no return value for the execute method, but you can use text execution listener to aggregate the results. Here the summary generating listener, a simple text execution listener that generates a summary of the test execution. Here a register test execution listener method, register one or more listeners for the text execution. Here the launcher here the test plan discover launcher discovery request method, discover test and build a test plan according to the supplied launcher discovery request by querying all registers engines and collecting their results. Here text execution summary, get summary, get the summary generated by the listener, and Here text the class the interface text execution summary is a summary of the test plan execution. Here register a listener for your choice. Here discover test and build test plan. Here execute test plan, and alternate to execute the request directly. Here the test plan describes the class test plan. Here the describes the tree of tests and containers as discovered by a launcher. As an example 6, we can consider this one, registering a test engine. For example, junit-jupiter-engine module registers it junit-jupiter-engine.jupyter-test-engine in a file name org.junit-platform-engine.test-engine within the /meta-info/services folder in the junit-jupiter-engine jar. Test engine registration is supported via Java service loader mechanism. As an example 7, we can consider registering a post discovery filter. For example, an example.custom tag filter class implementing post discovery filter and declared within /meta -inf/services org.junit.platform-launcher.post discovery filter file is loaded and applied automatically. Interface post discovery filter. Post discovery filter is applied to test descriptors after test discovery. In addition to specifying post discovery filters as part of launcher discovery request passed to the launcher API, post discovery filter implementations will be covered at runtime via Java service loader mechanism and automatically applied by the launcher in addition to those that are part of the request. As an example 8, we can consider this code segment, registering a launcher session listener. The interface launcher session listener register an implementation of this interface to be notified when a launcher session is opened and closed. This in the module org.junit.platform.launcher and package org.junit.platform.launcher. Registered implementation of launcher session listeners are notified when launcher session is opened before launcher first discovered and execute test, and close when no more test will be discovered and executed. They can be registered programmatically via launcher config that is part of the launcher factory, or they can be discovered at runtime via Java service loader mechanism and automatically registered with launcher session unless automatic registration is disabled. Tool support. Following build tools and IDEs are known to provide full support for launcher session: Gradle 4.6 and later, Maven, Surefire, Failsafe 3.0.0, M6 and later, IntelliJ IDEA 2017.3 and later. Other tools might also work but have not been tested explicitly. A launcher session listener is well suited for implementing once per JVM setup teardown behavior, since it's called before the first and after the last test in the launcher session respectively. The scope of the launcher session depends on the used IDE or build tool, usually correspond to the lifecycle of the test JVM. a custom listener that starts an HTTP server before executing the first test and stop it after the last test has been executed. Could look like this. Here you can see step 1 here, start server, and here you can see the export its host address as a system property for consumption by test, and export its port as a system property for consumption by test. And here stopped the HTTP server. The sample user HTTP server implementation from the JDK HTTP server module that comes with the JDK, but it would work similarly with any other server or resource. In order for the listener to picked up by JUnit platform, you need to register it as a service by adding a resource file with the following name and context to your test runtime class path. For example, by adding the file to source/test/resources. Here source/test/resources meta-info/services org.junit.platform.launcher session listener. And the example.session.global setup tear down listener. Now you can use the resource from your test. Here HTTP tests. Here read the host address of the server from the system property set by the listener, and read the port of the server from the system property by the listener. Send the request to the server and check the status code of the response. And here you can see avoid setup for test discovery by delaying until tests are about to be executed. Registering launcher discovery listener. The interface launcher discovery listener register a concrete implementation of this interface with the launcher discovery request builder or launcher to be notified events that occur during the test discovery. This is in the module org.junit.platform.launcher and package org.junit.platform.launcher. Here in addition to specifying discovery listeners as a part of launcher discovery request or registering them programmatically via the launcher API, custom launcher discovery listener implementations can be discovered at runtime via Java service loader mechanism and automatically registered with the launcher created via launcher factory. For example, an example.custom custom launcher discovery listener class implementing launcher discovery listener and declared within /meta-info/services junit.platform.launcher discovery listener file is loaded and registered automatically. As an example 10, we can consider registering test execution listener. For example, an example.custom test execution listener class implementing test execution listener and declared within the /meta-info/services junit.platform.launcher test execution listener file is loaded and registered automatically. The interface text execution listener register a concrete implementation of this interface with a launcher to be notified of event that occur during test execution. Module this is in the module org.junit.platform.launcher and package org.junit.platform.launcher. Here, in addition to launcher API method for registering test execution listeners programmatically, custom test execution listener implementation will be discovered at runtime via Java's service loader mechanism and automatically registered with the launcher created via launcher factory. As an example 11, we can consider junit.platform.execution.listener.deactivate. Here, deactivating a test execution listener. Sometimes it can be useful to run a test suite without certain execution listeners being active. For example, you might have a custom test execution listener that sends the test results to an external system for reporting purposes. And while debugging, you might not want these debugging results to be reported. To do this, provide a pattern for junit.platform.execution.listener.deactivate configure a parameter to specify which execution listeners should be deactivated that is not registered for the current test run. Only listeners registered via service loader mechanism within /meta-info/services/org.junit.platform.launcher.test unit test execution listener file can be deactivated. In other words, any test execution listener registered is explicitly via launcher discovery request cannot be deactivated via the junit-platform.execution.listeners.deactivate configuration parameter. In addition, since execution listeners are registered before the test run starts, the junit.platform.execution.listeners.deactivate configuration parameter can only be supplied as a JVM system property or via the JUnit platform configuration file. This configuration parameter cannot be supplied in the launcher discovery request that is passed to the launcher. As an example 12, we can consider configuring the launcher. The interface launcher config launcher config defines the configuration API for creating launcher instances via the launcher factory. This is in the module org.junit.platform.launcher and package org.junit.platform.launcher.core. If you require fine-grained control or automatic detection and registration of test engines and listeners, you may create an instance of launcher config and supply that either to the launcher factory. Typically, an instance of a launcher config is created via the built-in Fluent builder API as demonstrated in this example here. Here, launcher config the builder create a new launcher config builder. Here the method test engine enable test engine auto registration in launcher config.builder class. Configure the auto registration flag for test engines. Here the enable launcher session listener auto registration. Configure the auto registration flag for the launch session listeners. Here enable launcher discovery listener auto registration. Configure the auto registration flag for launcher discovery listeners. Here enable post discovery filter auto registration. Configure the auto registration flag for the post discovery filters, and here enable text execution listener auto registration boolean. Configure the auto registration flag for the text execution text listeners. Here add test engines. Add all the support supplied test engines to the configuration. Here add launcher session listeners. Add all the supplied launcher session listeners to the configuration. Add launcher discovery listeners. Add all the supplied launcher discovery listeners to the configuration. Add post discovery filters. Add all the supplied filters to the configuration. And add test execution listeners. Add all the supplied test execution listener to the configuration. And the build the launcher config that has been configured via the builder. As an example, now we are considering a usage example in discovering testing junit-platform-launcher API. Launcher discovery request. The interface in package org.junit-platform.launcher in module org.junit-platform.launcher. The launcher discovery request extend the engine discovery request API with additional filters that are applied by the launcher itself. Having test discovery as a dedicated feature on the platform itself frees the IDEs and build tools from most of the difficulties they had to go through to identify test classes and test methods in previous versions of JUnit. You can select classes, methods, and all classes in a package. Or even search for all tests in a class path or module path. Discovery takes a place across all participating test engines. Resulting test plan is a hierarchical read-only description of all engines, classes and test methods that fit the launcher discovery requests. The client can traverse the tree, retrieve details about the node, and get a link to the original source like class, method, or file provision. Every node in the test plan has a unique ID that can be used to invoke a particular test to a group of tests. Clients can register one or more launcher discovery listener. Implementations via launch discovery listener, launch discovery request builder to gain insight into events that occur during test discovery. By default, the builders registers a abort on failure listener that aborts the test discovery after first discovery failure is encountered. The default launcher discovery listener can be changed via the junit.platform.discovery.listener.default configuration parameter. Discover additional test plan, so execute tests. Now we are considering executing test. Test progress and reporting can be achieved by registering one or more test execution listener. Implementation with the launcher as in the following example. The interface launcher in module in package org.junit.platform.launcher in module org.junit.platform.launcher. The launcher API is the main entry point for launch for client code that wishes to discover and execute tests using one or more test engines. Here the void execute launcher discovery request here the launcher discovery request execution listeners execute the test plan which is built according to the supplied launcher discovery request by querying all the registers engines, collecting their result and notify the registers listeners about the progress and result of the execution. Void execute test plan execution listeners execute the supply test plan and notify the registers listeners about the progress and the result of the execution. To execute test, client can use the same launcher discovery request. As in a directory page, so create a new as in the discovery page, so create new request. Test progress and reporting can be achieved by registering one or more text execution listener. Test execution listener implementation with launcher as in the this example. There is no return value for the execute method, but you can use test execution listener to aggregate the result. For example, see summary generating listener, legacy XML report generating listener, and unique ID tracking listener. All test execution listener methods are called sequentially. Methods for start events are called the registration order, while methods for finish events are called in the reverse order. Test case execution won't start before all execution is started. Calls have returned. Register a listener of your choice. discover, test, and build a test plan. Execute test plan. Alternatively, execute the request directly. Do something with the summary. Now we are considering registering a test engine. Here the registering test engine registration is supported by a Java service loader mechanism. Here the class service loader type parameters in package java.util, in module java.base, a facility to load the implementation of a service. Now we are considering registering a post discovery filter. In addition to specifying post discovery filters as part of launcher discovery request passed to the launcher API, post discovery filter implementation will be discovered at runtime via Java service loader mechanism and automatically applied by the launcher in addition to those that are part of the request. Interface post discovery filter in package org.junit-platform-launcher, in module org.junit-platform-launcher. A post discovery filter is applied to test descriptors after test discovery. For example, an example.custom tag filter class implementing post discovery filter is declared within /meta- -inf/services/ org.junit.platform.launcher.post discovery filter file is loaded and applied automatically. Now we are considering usage example usage in registering a launch session listener, a custom listener that starts HTTP server before executing the first test and stop after the last test has been executed could look like this. The interface launcher session listener in package org.junit-platform.launcher, in the module org.junit-platform.launcher, register an implementation of this interface to be notified when a launcher session is opened and closed. Launcher session listener is well suited for implementing once per JVM setup and tear down behavior, since it's called before the first and after the last test in the launcher session respectively. The scope of a launcher session depends on the IDE, the used IDE or build tool what usually correspond to the lifecycle of test JVM. A custom listener that start an HTTP server before executing the first test and stop after the last test has been executed. This could like this. Here the started the HTTP server. Here the export the host address as system property for consumption by tests. Here the export its port as a system property for consumption by tests. Here the stop the HTTP server. This example is a HTTP server implementation from the jdk.http server module that comes with the JDK, but would similarly with any other server or resource. In order for the listener to be picked up by the JUnit platform, you need to register it as a service by adding the resource file while following the name and content to your test runtime class path, for example, by adding the source file to src/test for src resources. For src/test/resources/meta-inf/services/org.junit.platform-launcher session listener. Here the added line. Now you can use the resource from your test here. Here the read the host address and the server address and the server from the system property set by the listener. Read the port of the server from the system property set by the listener. And here the send a request to the server. Here the check the status code of the response. Avoid setup for test discovery by delaying it until tests are about to be executed. Now we are considering registering in launcher interceptor. In order to intercept creation of instances of launcher and launcher session listener and calls the discover and execute method of the former, and client can register custom implementation of launch interceptor via Java service loader mechanism by adding the setting. Additionally, setting the junit-platform-launcher.interceptor.enabled configuration parameter to true. A typical use case is to create a custom replace for class loader used by the JUnit platform to load classes and engine implementations. Now we are considering registering a launcher discovery listener. For example, an example dot custom launcher discovery listener class implementing launcher discovery listener and declared within the /meta-info/services/org.junit.platform.launcher.launcher discovery listener. File is loaded and registered automatically. In addition to the specifying listeners as part of the launcher discovery request to registering them programmatically via launch API, the custom launcher discovery listener implementations can be discovered at runtime via service loader mechanism and automatically registered with the launcher created via launcher factory. The interface launcher discovery request in package org.junit-platform-launcher in module.org.junit-platform-launcher. Launcher discovery request extend the discovery engine discovery request API with additional filters that are supplied by the launcher itself. Now we are considering registering a test execution listener. For example, example.custom test execution listener class implementing test execution listener and declared within the /meta-info services org.junit.platform.launcher.txt execution listener file is loaded and registered automatically. The interface test execution listener in package org.junit.platform.launcher in module org.junit-platform-launcher register concrete implementation of this interface with the launcher to be notified of event that occur during test execution. In addition to the public launcher API method for registering test execution listeners programmatically, custom test execution listener implementation will be discovered at runtime via Java service loader mechanism and automatically registered with this launcher created via the launcher factory. Now we are considering configuring a test execution listener. The listener can then access the configuration parameters via the test plans applied to the test plan execution started, test plan and test plan execution finished, test plan callback methods, interface test execution. The method default void test plan execution started test plan in interface test execution listener in package org.junit-platform.launcher in module org.junit-platform.launcher called when the execution of a test plan has started and before any test has been executed. When a test execution listener is registered programmatically via the launch API, the listener may provide programmatic ways for it to be configured, for example, via its constructor, setup methods, etc. However, when the test execution listener is registered automatically via the Java service loader mechanism, there is no way for the user to directly configure the listener. In such cases, the author of the test execution listener may choose to make the listener configurable via configuration parameters. Listener can then access the configuration parameters via test plans applied to the test execution started test plan and test execution finished test plan callback methods. See the now we are considering deactivating test execution listener. To do this, provide the pattern for the junit-platform-execution.listeners.deactivate configuration parameter to specify which execution listener should be deactivated that is not registered for the current test run. Sometimes it can be useful to run a test suite without certain execution listeners being active. For example, you might have a custom test execution listener that sends the test results to an external system for reporting purpose, and while debugging you might not want the debug result to be reported. To do this, provide the pattern for junit.platform.execution.listeners.deactivate configuration parameter to specify which execution listener should be deactivated that is not registered for the current test run. Only listeners registered via service loader mechanism with the method /method inf services org.junit-platform.launcher.test execution listener file can be deactivated. In other words, any test execution listener registered explicitly via launcher discover request cannot be deactivated via junit.platform.execution.listeners.deactivate configuration parameter. In addition, since execution listeners are registered before the test run restarts, junit.platform.execution.listener.deactivate configuration parameter can only be supplied as a VM system property or via junit-platform configuration file. This configuration parameter cannot be supplied at the launcher discovery request that is passed to the launcher. Now we are considering configuring the launcher. Typically, an instance of launcher config is created via the built-in Fluent build API as demonstrated in this example. The interface launcher config in package org.junit-platform.launcher.co in module org.junit-platform.launcher. Launcher config defines the configuration API for creating launcher instances via the launcher factory. If you require fine-grained control over automatic detection and registration of test engines and listeners, you may create an instance of launcher config and supply that to the launcher factory. Typically, an instance of launcher config is created via the built-in Fluent build API as demonstrated in this example. Now we are considering dry run mode. When running test via the launcher API, you can enable dry run mode by setting the junit.platform.execution.dryrun.enabled configuration parameter to true. In this mode, the launcher will not actually execute any test that will notify registered execute any test, but will notify test execution listener instances as if all test has been skipped and their container has been successful. This can be useful to test changes in the configuration of build and to verify the listener is called as expected without having to wait for all tests to be executed. Now we are considering the use of Maven Surefire failsafe 3.0.0 M4 or later to avoid interoperability issues in Maven in build support in running tests. Maven Surefire or failsafe 3.0.0 M4 introduce support for aligning the version of the junit-platform-launcher. It uses the junit-platform version found on the test runtime class path. Therefore, it is recommended to use version 3.0.0 M4 or later to avoid interoperability issues. Alternatively, you can add the test dependency on the matching version of the junit-platform-launcher to your Maven build as follows here. Now we are considering junit-platform in dependency metadata. The artifact ID junit-platform-launcher in group ID org.junit.platform. Public API for configuring and launching test plans typically used by the IDEs and build tools. You can consider this one occurred in IntelliJ and Spring Boot 2.3.9. Failed to resolve junit-platform-launcher 1.6.3 IntelliJ. Now we are focusing on junit-platform-runner. junit-platform-runner. Runner for executing test and test suites on JUnit platform in a JUnit 4 environment. And here you can see the runner hierarchy. A runner has to implement two methods of defining the cooperation policy with the tool's runtime instance. The first is get description. It is inherited from its super interface describable and returns the instance of the description. The description is used to provide human readable information about the test which is to be run or has been run. It can describe single test, atomic or a hierarchy of test compound. The information provided by each runner is used, for example, by GUI to depict all test that particular launch effect. The second method is called run, and it takes run notifier as an argument. This is of course where all the action happens. Here the runner is supposed to select the executables of test case, invoke them and report appropriate state information using notifier callback. We will provide more insight into this in a minute when we write our own implementation. Runner has to be abstract class. It supplies the convenient test count method. The latter provides the number of tests to be run, calculate on the information returned by get description. This enables subclasses to override the computation for unusual demand, but probably only seldom makes sense. At tiny rate, this base class is the way to go if you need functionality that differs significantly from the common use cases. More likely though is that one will extend parent runner T a subclass runner This implements the policy described earlier by delegating a few abstract methods, essentially an interior works on a list of children. The child is a generic type T. The list of T might be the test defined by a single test case. It should be derived from the constructor injected test class. Development needs are reduced to retrieve this list of children. And to provide description and execution of a single child. Parent runner class itself is responsible, among other things, for invoking the at before class and at after class annotated methods, creating a composite description and running children sequentially. The annotations are meant to share expensive fixture setups among the children. Thus marked method get only called once, namely after entirely of child executions. We are already aware of the block JUnit-4 class runner extension, which is used as a standard JUnit test case processor. Following diagram also contains another execution called suit that will cover the suit. And other than once mentioned, the class hierarchy contains two interfaces declaring filtering and sorting capabilities implemented by parent runner. But before here they describe this runner implements describable interface, and parent runner T implements the filterable and sortable, and implements runner, and here the suit and block JUnit for class runner is connected to parent runner here. As an example in Maven, we can consider this segment. Here you can see the artifact ID junit-platform-runner. This is in the group ID org.junit.platform. As an example 2, we can consider module org.junit.platform.runner and annotations for configuring and executing test on the JUnit platform in JUnit-4 environment. As an example 3, we can consider using JUnit-4 to run JUnit platform single test class JUnit platform JUnit-4 based runner, which runs test on the JUnit platform in JUnit-4 environment, deprecated since 1.8 in favor of the suit support provided by the JUnit platform suit engine module, to be removed in JUnit platform 2.0 module. It is in the module org.junit.platform.runner, package org.junit.platform.runner. Here one way to use the JUnit platform runner is to annotate a test class with ampersand run with JUnit platform.class directly. Please note that the test methods with the following examples are annotated with org.junit.jupiter.api.test junit-jupiter, not org.junit.test junit-4. Moreover, in this case, the test class must be public. Otherwise, some IDEs and build tools might not recognize it as a junit4 test class. The JUnit platform runner has been deprecated. The JUnit platform runner was developed by JUnit team as a interim solution for running test suites and test on the JUnit platform in a JUnit 4 environment. In recent years, all mainstream build tools and IDEs provide built-in support for running tests directly on the JUnit platform. In addition to the introduction of emphasized suite support by the junit-platform-surefire-engine modules make the JUnit platform runner obsolete. The JUnit platform runner and emphasized use technical names annotation have therefore been deprecated in JUnit platform 1.8 and will be removed in JUnit platform 2.0. If you are using JUnit platform runner, please migrate to emphasized suite support. JUnit platform runner is a JUnit 4 based runner which enables you to run tests whose programming model is supported on the JUnit platform in a JUnit 4 environment. For example, junit-jupiter test class. Annotating the class with run with emphasize run with and junit-platform.class allows it to be run with IDEs and built systems that support JUnit 4 but not yet support the JUnit platform directly. Since JUnit platform has features that JUnit 4 does not have, the runner is only able to support subset of JUnit platform functionality, especially with regard to reporting. The annotation type run with, when a class is annotated with ampersand run with or extend the class annotated with ampersand run with, JUnit will invoke the class it references to run the test in that class instead of the runner built into JUnit. We added this feature late in the development. While it seems powerful, we expect the runner API to change as we learn how people really use it. Some of the classes that are currently internal will likely be refined and become public. For example, suites in JUnit 4 are built using run with and a customer runner name suite. This description is with JUnit 4. We can consider this code segment as example 4, using JUnit 4 to run the JUnit platform test suite. If you have multiple test classes, you can create a test suite as can be seen in the following example. The annotation interface select packages, emphasize select packages specifies the names of packages to select when running a test suite on the JUnit platform. Using the module org.junit.platform.suite.api and package org.junit.platform.suite.api. Emphasize suite display name is used to declare custom display name for the annotated test class that is executed as a test suite on the JUnit platform. As an example 5, we can consider this using JUnit 4 to run the JUnit platform setup. You need the following artifacts and their dependencies on the class path. Explicit dependencies: JUnit platform runner in test scope, location of the JUnit platform runner, JUnit 4.13.2.jar in the test scope to run the test using JUnit 4, junit-jupiter-api in the test scope API for writing test using junit-jupiter including emphasized test, etc. junit-jupiter-engine in test runtime scope, implementation of test engine API for JUnit-Jupiter, Transitive dependencies, JUnit platform suite API in test scope, JUnit platform suite commands in test scope, JUnit platform-launcher in test scope, JUnit platform-engine in test scope, JUnit platform commands in test scope, open test 4j in test scope. Now we are considering explicit dependencies in setup in using JUnit 4 to run the JUnit platform. JUnit platform runner in test scope, location of the JUnit platform runner, JUnit here the 4.13.2.jar in test scope to run JUnit test using JUnit 4. junit-jupiter-api in test scope, API for writing test using junit-jupiter including at test etc. junit-jupiter-engine in test runtime scope, implementation of the test engine API for junit-jupiter. Now we are considering display names versus technical names. To define the custom display name for test class, run via run with junit platform.class, annotate with the class at display name and provide the custom value. The annotation interface suit suit display name in package junit-platform-surefire-provider in module junit-platform-surefire-provider. At suit display name is used to declare a custom display name for annotated test class that is executed as a test suit on the JUnit platform. Annotation interface use technical name in package junit-platform-surefire-provider in module junit-platform-surefire-provider. It's deprecated since 1.8 in favor of the suite support provided by the JUnit platform suite engine module to be removed from in the JUnit platform 2.0. At use technical names, specify that technical names should be used instead of display names when running test suite on the JUnit platform. By default, display names will be used for test artifact. However, when the JUnit platform runner is used to execute test with the build tool such as Gradle or Maven, the generated test report often needs to include the technical names of the test artifacts. For example, fully qualified class names instead of shorter display names like simple name of a test class or custom display name containing special characters to enable technical name for reporting purposes. Declare at use technical names annotation alongside run with JUnit platform.class. Note that the presence of at use technical names overrides any custom display name configured via at suit display name. Now we are considering single test class. Moreover, with this case, the test class must be public. Otherwise, some IDEs and build tools might not recognize it as a JUnit 4 test class. The annotation type run with org.junit.runner, and this is in the version 4. When the class annotated with at run with and extend a class annotated with at run with, the JUnit invoke the class references to run the test in that class instead of the runner built into JUnit. We added this feature late in development. While it seems powerful, we expect the runner API to change as we learn how people really use it. Some of the classes that are currently internal will likely be refined and become public. For example, suite in JUnit 4 are built using run with and custom runner named suite. One way to use the JUnit platform runner is to annotate the test class with at run with then JUnit platform.class directly. Please note that the test method in this example are annotated with JUnit org.junit.jupiter.api.test junit-jupiter, not org.junit.test in JUnit 4. Moreover, in this case, the test class must be public. Otherwise, some IDEs and build tools might not recognize it as a JUnit 4 test class. no op. Now we are considering test suite. If you have multiple test classes, you can create test suite as test suite as can be seen in this example. The annotation type select packages in package org.junit-platform-suite.api module org.junit-platform-suite.api. At select packages, specify the names of the packages to select when running a test suite in the JUnit platform. If you have multiple test classes, you can create test suite as can be seen in this example. The JUnit platform suite demo will discover and run all tests in the example package in its sub packages. By default, it will only include test classes whose names either begin with test or test or end with test or tests. Additional configuration options. There are more configuration options for discovering and filtering tests than select packages. Please consult the java doc for junit-platform-suite.api package for further details. The test class and suites annotated with run with JUnit platform .class cannot be executed directly on the JUnit platform or as a JUnit 5 test as documented in some IDEs. Such classes and suites can only be executed using JUnit 4 in file structure. Now we are considering the JUnit platform in dependency metadata. Artifact ID JUnit platform runner in group ID of the JUnit platform runner for executing test and test suites on the JUnit platform as in JUnit 4 environment. As an exception example, we can consider this no test remain exception. Can be occurred in method void public void filter in class JUnit platform. As an example, we can consider this occurred in environment with Eclipse and Maven. Package org.junit.platform.runner does not exist, etc. Now we are focusing on JUnit platform-surefire-provider. JUnit platform-surefire-provider, which provides a support for discovering and executing tests on the JUnit platform by using Maven Surefire. As an example in Maven, we can consider this one. Artifact ID JUnit platform-surefire-provider. The group ID org.junit.platform. The JUnit platform Maven Surefire-provider has been discontinued. The JUnit platform Surefire-provider, which was originally developed by the JUnit team, was deprecated in JUnit platform 1.3 and discontinued in 1.4. Please use Maven Surefire native support instead. Starting with version 2.22.0, Maven Surefire and Maven failsafe provide native support for executing tests on the JUnit platform. The pom.xml file in the JUnit Jupyter Starter Maven project demonstrate how to use Maven Surefire plugin and can serve as a starting point for configuring your Maven build. As an example too, we can consider package org.junit.platform.surefire.provider, Maven Surefire provider for JUnit platform. As an example 3, we can consider this the Maven, this Maven segment. Here you can see JUnit platform-surefire-provider here. Here you can see the Maven Surefire provide in build support in running test. In here the use of configuration parameters property. Now we are focusing on JUnit-platform-gradle-plugin. JUnit-platform-gradle-plugin, which provides support for discovering and executing tests on the JUnit platform by using Gradle. The JUnit-platform-gradle-plugin has been discontinued. The JUnit-platform-gradle-plugin developed by the JUnit team was deprecated in the JUnit platform 1.2 and discontinued in 1.3. Please switch to Gradle standard test task. As an example, we can consider this. Here you can see artifact ID JUnit-platform-gradle-plugin here. It's under group ID org.junit.platform. As an error example, we can consider this error occurred in environment Gradle version 4.0. Plugin with ID org.junit.platform.gradle.plugin not found. Platform console, support for discovering and executing tests on the JUnit platform from the console. Here you can see the artifact JUnit platform console, the group ID org.junit.platform. As an example, too, we can consider org.junit.platform.console module, support for launching the JUnit platform from the console. As an example 3, you can also run the standalone console launcher as shown here. For example, to include all jars in a directory. Yeah. Exit code, the console launch exit with the status code of 1 if any containers or test fails. If no tests are discovered and the --fail if -node -test command line option is applied, the console launcher exits with the status code of 2. Otherwise, exit code is 0. The class console launcher. The console launcher is a standalone application for launching JUnit platform from the console. It's in the module org.junit.platform.console and package org.junit.platform.console. The console launcher is a command line Java application that lets you to launch the JUnit platform from the console. For example, it can be used to run junit-vintage-engine Jupyter test and print test execution results to the console launcher. Argument files, ampersand files. If an argument contains embedded white space, the whole argument should be wrapped in a double or single quotes, for example. And options selectors -f or -- select -file equal file. Select file for test discovery. This option can be repeated. On some platforms, you may run into system limitation of length of the command line when creating command line with lot of options, so with long argument. Since version 1.3, the console launcher supports argument files, also known as ampersand files. Argument files are files that themselves contain arguments to be passed to the command. When the underlying Picocly command line parser encounters an argument beginning with the character ampersand. It expands the contents of that file into the argument list. If the argument file does not exist or cannot be read, the argument will be treated literally and will not be removed. This will likely result in unmatched argument error message. You can troubleshoot such errors by executing the command with the pico.cli.trace system property set to debug. Multiple ampersand files may be multiple @signs may be specified on the command line. Specified path may be related to the current directory or absolute. You can pass real parameter with the initial @character by escaping with the additional @symbol. For example, at some mark will become @some mark and will not be subject to expansion. As an example 5, we can consider color customization, the console launcher. The properties file here demonstrate the default style. The single color style test output using only text attributes, no color, not supported by all terminals. --color-palette equal file specify a path to a properties file to customize ANSI style of output, not supported by all terminals. The colors used in the output of the console launcher can be customized. The option --single color will apply a built-in monochrome style, while --color-palette will accept the properties file to override ANSI SGR color styling. The properties file here demonstrate the default style here. Successful equal 32, aborted equal 33, failed equal 31, skipped equal 34, 35, container equal 35, test equal 34, dynamic equal 35, and reported equal 37. Now we are considering class console launcher in package junit-platform-console in module log.junit-platform-console. The console launch is a standalone application for launching the JUnit platform from the console. Here we are considering console launch in running test. You can run the standalone console launch as shown here. The console launcher is a command line Java application that lets you launch the JUnit platform from the console. For example, it can be used to run JUnit vintage and junit-jupiter test and print test execution results to the console. The executable JUnit platform console standalone 1.10.0.jar with all dependencies included is published in Maven Center repository under JUnit platform console standalone directory. You can run the standalone console launcher as shown here. You can also run the standalone console launcher as shown here, for example, to include the old jars in a directory. Exit code, the console launcher exit with the status code of 1 if any containers or tests failed. If no tests are discovered and the --fail if no tests command line option is applied, the console launcher exit with the status code of 2. Otherwise exit code is 0. JUnit, now we are considering subcommands and options. The console launcher provides the following subcommands. Now we are considering argument file at dash files. If an argument contain embedded white space, the whole argument should be wrapped in double or single quotes. For example, here dash f equal my space files /stuff.java double quotation here. On some platforms you may run into system limitations on the length of the command line and creating command line with a lot of options, so with long arguments. Since version 1.3, the console launcher support argument files, also known as at dash files. Argument files are files that themselves contain argument to be passed to the command. When underline Peacockly command line parser encounters an argument beginning with the character at, it expands the content of the file into argument list. Arguments within a file can be separated by spaces or new lines. If an argument contains embedded white space, the whole argument should be wrapped in double or single quotes, for example, like here. If the argument file does not exist and cannot be read, the argument will be treated literally and will not be removed. This will likely result in an unmatched argument error message. You can troubleshoot such errors by executing the command with Peacockly.trace system property set to debug. Multiple at dash files may be specified on the command line. The specified path may be relative to the current directory or absolute. You can pass the real parameter with an initial at character by escaping it with the additional at symbol. For example, at some arg will become at some arg and will not be subject to expansion. Now we are considering color customization. The colors used in output of the console launcher can be customized. The option color single color will apply a built-in monochrome style, while color palette will accept the properties file to override SGR color styling. The properties file below demonstrate the default style. And now here we are considering open test reporting console launcher in open test reporting XML in JUnit platform reporting. When using the console launcher, you can enable open test reporting output by setting the configuration parameter via --config here. Now we are considering the JUnit platform independency metadata, the artifact ID JUnit platform console in group ID org.junit.platform, the support for discovering and executing tests on the JUnit platform from console. This occurred in the environment with 5.0.0 and operating system and version Mac OS X 10.15.7 Catalina x86-64 build tools Gradle 6.8.3 Kotlin 1.4.30 JVM 11.0.10 and this is caused by Java lang. The console launcher test failed. The error could not find or load main class org.junit.platform.console.console launcher caused by java.lang.console class not found exception org.junit.platform.console.console launcher. Follow the steps for readme .md #cucumber junit-platform-engine. Step 2, assume incorrectly that only dependency needed is org.junit.platform colon junit-platform-launcher xyz run /gradle clean test and observed error. As an error example, we can consider this occurred in the environment with JMeter and MSSQL-JDBC. Failure to find org.junit.platform junit-platform-console jar in https://repo.maven.apache.org./maven was cached in the local repository. Resolution will not be reattempted until the update interval of central has lapsed or updates are forced. Now we are focusing on IDEs, build tools. An integrated development environment, IDE, is a software application that provides comprehensive facilities to computer programmers for software development. An IDE normally consists of at least a source code editor, built automation tools, and a debugger. Some IDEs such as NetBeans and Eclipse contain the necessary compiler, interpreter, or both. Others such as Sharp Develop and Lazarus do not. Build automation is the process of automating the creation of a software build and associated process, including compiling computer source code into binary code, packaging binary code, and running automated tests. As an example, we can consider IntelliJ IDEA. The IDE support. IntelliJ IDEA supports running tests on the JUnit platform since version 2016.2. Note, however, that it is recommended to use IDEA 2017.3 or newer, since these newer versions of IDEA will download the following jars automatically based on the API version used in the project: junit-platform-launcher, junit-jupiter-engine, and junit-vintage-engine. IntelliJ IDEA releases prior to IDEA 2017.3 bundle specific versions of JUnit 5. Thus, if you want to use a newer version of JUnit-Jupiter, execution of tests within the IDE might fail due to the version conflicts. In such cases, please follow the different instruction to use newer version of JUnit 5 than the one bundled with IntelliJ IDEA. In order to use different JUnit 5 version, for example 5.9.0, you may need to include the corresponding versions of the junit-platform-launcher, junit-jupiter-engine, and junit-vintage-engine jars in the class path. As an example too, we can consider additional Gradle dependencies in IntelliJ IDEA here. As an example 3, we can consider Eclipse. Eclipse IDE offers support for the JUnit platform since the Eclipse Oxygen 0.1a 4.7.1a release. You can see the execution of test here. NetBeans, as an example 4, we can consider NetBeans. NetBeans offers support for JUnit Jupyter and JUnit platform since Apache NetBeans 10.0 release. As an example 5, we can consider Visual Studio Code. Visual Studio Code supports JUnit Jupyter and the JUnit platform via the Java Test Runner extension, which is installed by default as a part of the Java extension pack. As an example 6, we can consider Gradle build support here. Starting with version 4.6, Gradle provides native support for executing test on the JUnit platform. To enable it, you need to specify use JUnit platform within a test task declaration in the build.gradle junit-platform-gradle-plugin has been discontinued. The junit-platform-gradle-plugin developed by the JUnit team was deprecated in junit-platform 1.2 and discontinued in 1.3. Please switch to Gradle standard test task. As an example 7 in Gradle, we can consider this one, configuring test engines. To configure support for the JUnit-Jupiter based test, configure a test implementation dependency on the dependency aggregating JUnit-Jupiter artifact, similar to the following here. In order to run any test at all, a test engine implementation must be on the class path. As an example 8, we can consider Maven. Starting with version 2.22.0, Maven Surefire and Maven Failsafe provide native support for executing tests on the JUnit platform. The pom.xml file in the JUnit 5 Jupyter Starter Maven project demonstrate how to use the Maven Surefire plugin and can serve as a starting point for configuring your Maven build. JUnit platform Maven Surefire-provider has been discontinued. The JUnit platform-Surefire-provider, which was originally developed by the JUnit team, was deprecated in JUnit platform 1.3 and discontinued in 1.4. Please use Maven Surefire native support instead. As an example 9, we can consider Maven configuring test engines. In order to have Maven Surefire and Maven Failsafe run any test at all, at least one test engine implementation must be added to the test class path. To configure support for JUnit-Jupiter based tests, test scope dependencies on the JUnit-Jupiter API and the JUnit-Jupiter test engine implementation, similar to following. As an example 10, we can consider Ant. Starting with version 1.10.3, Ant has unit launcher task that provides native support for launching test on the JUnit platform. The JUnit launcher task is solely responsible for launching JUnit platform and passing it to the selected collection of tests. The JUnit platform then delegates to registered test engines to discover and execute tests. As an example 11 in Ant, we can consider this segment, the basic usage. Here this example demonstrates how to configure JUnit launcher task to select single test class, that is org.myapp.test.myfirstJUnit-test. As an example 12, we can consider Spring Boot. Spring Boot provides automatic support for managing the version of JUnit used in your project. In addition, the Spring Boot starter test artifact automatically includes testing libraries such as JUnit-Jupiter, AspectJ, Mockito, etc. As an example 13, we can consider Spring Boot here. Configuration with Gradle. You can override the JUnit-Jupiter version by including this in your build.gradle file. As an exception example, we can consider this. In Eclipse, the test would be marked as passed even if the test method throws an exception, which is a subclass of the specified exception in the at test expected clause. As an exception example 2, we can consider this occurred in environment with Gradle and JUnit. Error Gradle org.gradle messaging org.gradle.messaging.remote.intel internal.hub.message hub backed object connection, unexpected exception thrown, etc. and caused by java.land.nullPoint exception at java.land.throwable set stack trace throwable at org.gradle.messaging.remote.internal message exception placeholder.read. As an error example, we can consider this occurred in the environment with IntelliJ IDEA, Maven, and JUnit 5 here. And you can see process finished with exit code -1 here. As an error example 2, we can consider this occurred in environment with Gradle. Here compile Java, users workload project gradling source test calculate test.java error package org.junit does not exist, etc. and here 5 errors and compile failed, failure, built failed with an exception, etc. This is end of my presentation. Thank you very much for watching it.